everybody, and thank you for coming. We have quite a good number of people, which in the end even caused some troubles. And at the University of Bern, all the events above 30 people have to be confirmed by the rectorate. And we found out that very late, and then we went to the rectorate, and we were rejected to organize this event with more than 30 people. And because of that, officially, then we shifted the organization to the University of Neuchatel, since the University of Neuchatel doesn't have these rules. But in the meantime, since a couple of people had to stay at home because of illness, and in our group also because of a positive test of someone who was vaccinated, we are now at 28, which would even allow to have it as University of Bern event in the meantime. And because of that and because of the rules, we have to be very strict. So therefore, we ask everybody to have a certificate to attend here, and we just have to be somehow fair and strict to everybody for attending this workshop here. So we have, I think, 6 sessions defined: today 2, tomorrow in the morning 2, and on Wednesday we should then be finished by noontime approximately. Tomorrow afternoon I hope the weather will be fine, and then we will organize a hiking tour. There's still some options. There's also a quite high mountain, but it takes 5 to 6 hours to go up and 3 hours to go down. It's a little bit strenuous probably, but we will find something. And in the evening tomorrow we will have a barbecue then here at the hotel. I want to in particular thank Antonio Di Maio, who has bothered all the students to provide abstracts and titles so that we can group somehow together the talks and have also mixed sessions. And I also thank to the senior people to take over then the organization of the sessions. And after thanking you for coming, I want to give the word to Antonio, who will chair the first session.
We start the first session titled Machine Learning for Wireless Networks. So we have 3 talks in this first session, and we welcome the first speaker on stage is Eric. Please come.
For the
Yes.
for the third presenter, that's Yann, who is getting his test.
Yeah, but
someone can switch. Can we ask?
We might as well finish the session a bit earlier because we started a bit late, and then we have him present in another session or tomorrow.
Oh, okay.
Because the session on Wednesday is going to be a bit lighter because some people could not attend. So we would have only 4 talks on Wednesday. So maybe he could present on Wednesday.
Yeah, that's good.
On Wednesday, I think we have a session about IoT and a session about data analytics, I think.
Okay.
So maybe since he's working with OLSR, with reinforcement learning, we could maybe fit him with the data analytics session. But we will see.
That's right.
Okay.
Okay. Common shift P.
Okay.
Yeah, here.
Hello, my name is Eric Samikwa. I'll talk about my topic on efficient distributed and federated machine learning for Internet of Things. This is the agenda for my talk. I'll give a background, and then I'll describe the problem. Then I'll talk about analytical computation, which is an area that we've been working on. and then I'll talk a little bit about some future work on federated split learning, and then I'll give the conclusions. As we know, Internet of Things generate massive amount of data because there are billions of devices, and this number is expected to grow to about 75 billion devices by 2025. And machine learning is a key tool in Internet of Things, which provides the ability to do advanced data processing. So this massive amount of data is well utilized using machine learning. The current status quo is that this machine learning implementation is cloud-centric. So we have to collect this data from these devices and send it to the cloud for processing. This has three main disadvantages. The first one is privacy, because we are transmitting this data over the network. It risks exposing it to attackers, but also storage. So we are storing this data in a central platform. This exposes the data to attackers. Another issue is latency. So transmitting this raw data from devices all around the world to this central platform for processing can cost a considerable amount of time, and this may not suit well with other latency sensitive applications. And another issue is network load. So because there is massive amount of devices, and massive amount of devices generate a lot of data, this can overwhelm the network, leading to a network load. So the vision is that we want to have this machine learning being implemented in a distributed and federated way, so that we are able to process data close to where it's generated. This has many benefits, including privacy and also latency and scalability, because we have reduced this bottleneck of central processing, and also reliability, because we have to factor in these networks of transmitting this data. If we're able to process somewhere close to where the data is generated, we get an improvement in reliability and eventually less network load. So in IoT, to implement this, there are key challenges. The first challenge to be able to do this is the computation and communication constraints. So we have devices which are resource constrained, such as limited memory and energy budget. But also we see that state-of-the-art machine learning models are demanding significant amount of resources to be able to operate in terms of memory and computation and energy. But we also have not to forget the privacy requirements. So the ways that we want to do this still more, we want to push the computation towards the devices, towards the edge, but we should also consider privacy and sensitive user information. So I'll talk about our work on early exit of computation, which is aiming at low latency and energy efficient collaborative machine learning inference. So in this way, we consider an area called DNN partitioning or model partitioning, where we consider a neural network as a sequential connection of several independent executable layers. So in this way, we have this big model. Now we go inside the model, and now we are looking at the layers. This allows us to be able to split the computation of a task between, for example, a device and a server. In this case, an edge server. So we can be able to complete the task, which is huge for this device, by just executing some of the layers on this device. So this, first of all, provides some layer of privacy, because we are instead of taking the raw data from the user, we are transferring data which is battery processed. So it's intermediate data from the layers. But also it has reduced the computational footprint on the device. So because we are computing not the full task. And we are computing the remaining task on the server. So here we see an example model, and for the model itself, we can be able to profile the computation time of each layer, but also each layer has varying amount of output data. Now, for example, if we consider that we want to see what is the end-to-end runtime of this task, then we have to consider the time it takes to compute the first layers on the device, and the time it takes to compute the intermediate data, and then the time it takes to compute on the server, for example. So we can add up this and be able to to compute the end-to-end runtime of this task. For example, here we see that we can split the model at different points, and we can be able to calculate this to see, depending on the data output we produce at that split layer, and see which one will lead to minimum runtime, end-to-end runtime. So here, like the blue part indicates the time it takes to compute on the device, and the orange part is the time it takes to transmit the intermediate data, and the green part is the time it takes for computation on the server. And we already see that there is a layer here that results in lower runtime. Before I go further into describing our approach, I want to talk about some application scenarios. So this can be applied in privacy and very sensitive applications where we have low resource environment on the device. So it could be image recognition, it could be smart health applications where we have very sensitive data, but also the device which is handling the computation close to the user is relatively low resource. And it has already been applied in industrial IoT applications where they are able to do collaborative inference between a detection camera and some central server in a way that the computation has been split between the two devices. But also in mobile environments where we have drones maybe detecting something or computing a certain machine learning task, and they're able to split the model between some fixed server and the mobile device. So this is the mechanism of our approach. So firstly, we have a phase where we detect the computation time. We profile the computation time of the model layers on the device and also on the server, and then we are able to we are able to use this information together with the available bandwidth or the network information to detect which position or which point is going to split the model for low energy or low latency. This one presents a sample model, and for example, we have a computation by this adaptive mechanism, and we have decided to split the model in that configuration, and then we can do collaborative inference. So the key features of this mechanism, first is adaptive. So it's adaptive to the available bandwidth for transmission. Sorry, I repeated adaptive. But also the second one, which is also important in this IoT setting, is energy consideration. So you could want to split this model to result in a completion of the task that is less energy consuming. But also another key feature is that because of this profiling process, we are able to get more accurate result for the optimization because we have an algorithm that first measures as a benchmark the performance of these layers on the specific hardware. here are some of the results. And here we see that the optimal split point to obtain low latency collaborative inference or low energy collaborative inference is varying depending on the available bandwidth, because the time it takes to transmit the intermediate data. So we have to consider that into the model. But also sometimes it is the same, which achieves latency and energy. Sometimes it is varying. So the experiment is we tested our optimizer in a dynamic network environment where we have different changes in the available bandwidth, and we compared it with other two solutions. So we have the first solution, Session, is more of a general solution which does close to the same, but in a general sense, while the other one, Boomerang, is more towards IoT. The difference is that the first one is not more adaptive, and the second one is a regression-based model, so they don't do this profiling, but also they have no consideration for the energy. And we see that our approach in blue, we're able to obtain the lower end-to-end runtime of the task compared to those existing approaches. But also it's relatively stable with changing network conditions. But also this can allow us to set a lower deadline for this task that the other ones cannot achieve. And we are obtaining about 25 up to 25% improvement over the existing approaches, and we're also obtaining about up to 40% less. Up to, sorry. Up to 40% less energy consumption compared to device-only computation. Lastly, I'll talk about federated split learning, which is our future week. So basically, split learning and federated learning are two technologies that are aiming at this vision of being able to complete the task towards the edge. So in split learning, it's basically an extension of the same DNA partitioning technique, but this one has more data being exchanged, where the model can be trained while it is separated over multiple devices, not in one device. While in federated learning, we have the model being in one place, so each client has a version of the model which best describes their data, and this can be aggregated somewhere on the server. So the key thing, the key components of the tool is that split learning allows training in low computation requirements, because we are only training part of the model, not the whole model, compared to federated learning. And also it has privacy, because no one individual machine has the full model, while federated learning has more scalability and also it has privacy. So there was a study which was conducted last year, and they compared the two technologies, and they see that for split learning, for federated learning, it works well when we have more clients but with less parameters, or less clients with more parameters, while split learning can work with while we have those two parameters high. And there was a paper last year which worked on combination of the two, with the aim of more privacy sensitive, but also be able to train in resource-constrained environments. So our current proposal on this one, we want to look at the combination of the two with a clustering technique that will help us be able to complete this training or distributed training in low resource environments, but also with more privacy consideration. This one was applied in health applications, and we aim to apply within the same field, but also make it general to other applications. In conclusion, we have seen that cloud-centric approach for machine learning in IoT systems has some drawbacks, and the vision is to more distributed and use the federated approach. The challenge is that we have low resource devices, but and also we have resource-hungry models. And we have looked at one of our work in LX computation, which is aiming at low latency and energy efficient collaborative machine learning. Thank you.
Thank you, Eric, for the talk. So now we can open like a Q&A session. So if you have any question for Eric, as for every other talk, they will last all 15 minutes, followed by a 10-minute period to ask questions and get replies. So if you want, anybody has questions for Eric?
Yeah, I have a question on slide 11. If you, well, it will help me to. Yeah, so this is here. I'm very surprised that we get oscillations with the bandwidth. I would expect that there would be like a turning point where below bandwidth you get some results as optimal, and then after this point another result. But these oscillations. But maybe if I'm getting right, is that the bandwidth that you have here, was it the measurement?
No, it was not a measurement. We set it intentionally to be changing to emulate an environment where the bandwidth is changing.
So this is what you have in the timestamp below. Then at each timestamp you have a different bandwidth.
Yeah.
Okay.
So we intentionally set it to oscillate.
But is it like a measurement, the optimal latency and energy, or is it the result of a model?
This is the measurement.
Oh, it's a measurement.
Yes. Yeah. So this side is a measurement, and this is this is like the experiment from it.
But
Yes.
I can follow because I had pretty much the same question. So this is everything here is evaluation on real devices. It's not simulation, right?
Yeah.
And so, what kind of devices do you consider exactly? I didn't get that.
Okay. So the experiment setup, we had some Raspberry Pi,
Okay, right.
and then a server,
Uh-huh.
and then we had we used the tool called Wonder Shaper to change the bandwidth between the two.
Okay, so and the Raspberry Pis, they communicate directly using Wi-Fi or wired system Wi-Fi.
Yes.
And one last question. So in the hierarchical cases, so you said that you have federated approach. Federated approach means some devices that they're not all equal, right?
Yes.
Do you consider something in which you would have, let's say, IoT and edge? You know, there's this in-between layer in which you have some slightly more powerful systems, or do you really consider something that have really even peer-to-peer communication between the IoT devices?
So the current experiments that we did, where we consider we have IoT device, and then we have the server. However, our model is measurement based, so basically we have to do a profiling of the model on the hardware, so it's hardware specific.
Okay.
So this can be taken into the model.
Mm-hmm.
Yeah, if we have different heterogeneous devices at different levels.
Okay. Yes.
Any other question? Yes.
Yes, you assume a feed-forward neural network, right? A CNN or something like that.
Yes.
Could you comment if your work is still valid if you have now a recurrent neural network? Is it still possible to do this exit strategy and so on?
Okay. So first, I think the idea of DNA partitioning model came into came in because specifically for sequential models.
Okay.
Especially, for example, here we are using CNN, which is a heavy model, and the impact of splitting this model is more significant. But I've not seen any work which has done in the sequential models like RNN, but I think that's an interesting area also to look at, because there might be some other RNN which are more heavy.
Thank you.
Any other question, please?
Thank you. Just one question with respect to this slide. Here on the right side with latency and energy, you have the blue line, the blue machine, that's current solution. What is meant by current solution?
So the current solution here means they are optimized in our way. So what we propose, I just labeled it as current solution. Yeah, so the blue one is the current solution is means our wake. Yeah, so didn't give it a specific name. That's why I just labeled it current solution.
Yes. So here composition and covering. So what do they do different compared to your approach? Can you summarize that, maybe?
Yeah. So
why are you better than those?
yeah. So the association is a more of a generic model, a generic optimizer, which is for DNA partitioning. It doesn't really target IoT or resource constrained devices, and it's less adaptive. How they design they optimize. While Boomerang is more of IoT, not so generic. It is also adaptive, but does not consider energy first. But also it uses a regression-based way. They don't use hardware profiling. So in our model, we profile, we have an algorithm that we profile on the hardware to get the data and feed into the optimizer. While for them, they use a regression to predict how the layer is going to perform on the device, and then they use that data into their optimizer.
Yes, please.
So here you assume that the topology, or I'm not too much into machine learning, so I don't know if I'm using the right word, but basically the design of the layers is fixed. Is it something you can't control? It's somebody gives you a network and you optimize for it.
Yeah. So
Yes.
you mean the layers of, just
Yes.
to understand the question, of the model, the machine learning model.
Yes.
Yeah. So the assumption is, as in many cases, we have a machine learning model which we have trained on. We want to use this model. Basically, after we have decided the hyperparameters,
Yeah.
we keep it. We don't change it,
It's given.
and then we use it several times.
But would it be possible to design one for split?
Or design like a new model for splitting.
Yes.
Yeah, that can be also interesting. So this like here we are looking at splitting existing models to fit into an architecture of devices. Yeah, another way could be designing models which are already split. That can be also interesting.
Thank you. Any other question there? Yes, please.
For clarification, what units do you use for the timestamps?
For the timestamps,
Yes,
is
it seconds or?
You mean here?
Yes.
Yeah, it's not necessarily seconds. It's we are trying to have a timestamp at an event where we have a different level of the bandwidth, but it's close to a second.
So this means that the timestamps are not necessarily even spaced. So it could be that the time period is either longer or shorter.
No,
Or they all the same?
we try to in a situation where they are even spaced.
Okay.
Yeah.
Another question is on the energy out, or what device did you use in order to measure the energy consumption of the Raspberry Pis?
So we use the plug-in energy monitor. So this device we can connect to a Raspberry Pi. We use the smaller Raspberry Pi A, and then we connect and we are able to read the energy consumption of the device.
Okay, any other last question? We have time for one more. No? Okay, then maybe I can ask one. We have worked already. So here I see you are basically simulating an environment in which the bandwidth between your IoT device and the server changes over time. So that's why we see this behavior like this. Since your work tends to optimize both the latency and the energy, keeping in mind the communication part, so that's why you change the bandwidth, but also the computation part, how would, and I know in your model you assume that the computation power is fixed over time, how would your optimization problem deal with also variable computation of a device, for example, which could be triggered by having some other services running on the device, or operating system routines that get called from time to time that might change the time required for each layer to output a prediction. So how does your model can be fit to cover this?
Okay, so I'll answer this in two ways. So first of all, generally for most of the devices on the user end, they are more specialized, and we see that they are handling mostly one task. And first of all, in the profiling, we first profile the device itself without handling any task. I know that for the server side, we could have difference in the computation time, but then the algorithm incorporates a method which can measure the time and then use this as an update to the existing benchmark data.
Okay. Okay, that's good. Then we are run out of time. So again, thank you, Eric, for your presentation. So now it's the time for our second speaker, is Lucas. And as usual, we have the 15 minutes followed by 10 minutes Q&A. So maybe you want to disable the screen, the screensaver, and just to. Yes.
Hello everyone, my name is Lucas Pacheco. I'll be presenting this work entitled Federated Learning over Vehicular Networks, or an opportunistic aggregation technique for federated learning over vehicular networks. And this is the agenda of my presentation. I'll give a brief introduction of the scenarios and the techniques that I'll be using during this work. I'll describe the architecture of the network and the entities that compose this work, and I'll describe the proposed algorithm, implementation steps, and the next steps in this research. So basically this work comes into a context in which machine learning becomes highly important in vehicular scenarios, especially with the rise of research in autonomous vehicles, in which you need to perform several artificial intelligence tasks, such as image classification, mobility prediction, objects detection from images. And these are all tasks that require a heavy amount of data to train robust machine learning models. However, they are very privacy-sensitive tasks. So if a vehicle captures some camera images, naturally they don't want to share these images with other vehicles or even with network entities that could use these images to compromise the user privacy. So in this context, like Eric mentioned briefly, federated learning comes as a collaborative and privacy-aware training of machine learning models, which is exactly a great fit for this vehicular AI problem. So this is a simple illustration of a federated learning process. Like it was mentioned, in the federated learning process, you create a global machine learning model architecture, which is to be used by every client in the network, and you transmit this architecture to the end devices themselves, which possess the data from which you want to train the model. And this is associated with some objective function, which is usually given in terms of the loss or the prediction error for this model. So each device in the network will perform the training over their local data sets, and instead of sharing their own raw data with the network or with other devices, they only share the trained neural network weights, which is then averaged normally, which is called a federated averaging process. And you can show that this converts into a machine learning model that's equivalent to one trained with the raw data from all users. So this process can be described in terms of a few components. For example, its participants. It is not always necessary for every user in the network to participate. Perhaps they have poor connections, which will slow down the process, or they will have poor quality data. The aggregation technique, which is usually very simplistic, based only on averaging the weights. However, this falls into some problems of averaging data with different statistical features, which will decrease the overall performance of the network. The objective of the model in terms of the loss function that you define, for example, if you have some labeled data for object recognition, then your loss function could be the prediction of bounding boxes in images. And of course, this is a process heavily shaped by network conditions. So if the network conditions are poor, you will have limitations, for example, over the number of parameters that you can aggregate and transmit through the network. And another great limitation, that is what I try to address with this work, is the synchronicity of this process. So this is the basic flow of the federated learning process, in which it distributes the global model to users, they train the model, they return it to a central service. So you can see this is a very synchronous process. And if you have for at least one participant user with a poor connection, they can slow down the aggregation process for the entire network, as the network will be kept waiting for this user to train the weights and transmit it. So in this context, especially over vehicular network, you have some very specific network conditions that offer some opportunities and challenges to the process. So for example, if you want to perform some peer-to-peer communication for this aggregation, you have to deal with the high mobility of vehicles and short contact times, but it's still a good opportunity for the process because vehicles are capable of V2X communication. In other words, they can communicate with other vehicles or with the network infrastructure. However, in traditional federated learning, you only communicate with network infrastructure. If you have peer-to-peer communication, you can actually define strategies to aggregate models between two vehicles, and thus you can get some steps ahead in the process, the entire process. So, yeah. So basically the federated learning is given in terms of this loop in which you transmit the model to the users, they perform updates, report back, and you repeat this until your model converges to a stable loss. However, what we would like to propose is a heavily distributed and opportunistic federated learning process in which you still have to define a global architecture for the model, you distribute it to vehicles. However, when vehicles come into contact, they can transmit the weights directly among themselves. Perhaps if it's in an area of the network with poor coverage from the infrastructure. And thus, when one of these vehicles connects to the infrastructure, they can pass these updates to the network to be passed on to other vehicles. So basically, this is a contact-based aggregation, and I will explain a little more how it works. So basically, we've defined this algorithm. I'll just brush through it. So we still need to define a neural network model architecture in terms of a loss function, which is usually to minimize the loss for every vehicle, for every data sample, given that every vehicle will have the same model, neural network model. So this is distributed to vehicles from the infrastructure or from other vehicles after this architecture has been decided, and that's another research problem. Vehicles will train this data, and upon contact with the network infrastructure or with other vehicles, they will transmit the neural network weights which they have trained, and this is added to a modified model entity which we defined, which is composed not only of the neural network weights with the actual numeric parameters that are used for predictions, but actually a history of the contributions from every vehicle. So in this context, when vehicles meet, they have a list of contributions which they compare, and they can exchange the diff from this list. And we can show later that this is actually equivalent to a traditional federated learning aggregation, however, in a shorter time. So in a traditional neural network, this is a randomly generated graph. So we can talk about the communication aspect of the network. Just check my time. And we can see that in a network you can have some isolated clusters of vehicles which can communicate. So the edges on this graph are representing communication links. Even if we consider a very simple static scenario, if we disconsider the vehicle mobility, perhaps because of the training process happens in a much shorter time span than vehicle mobility, if we make this assumption, we have actually several isolated models in the network. And an interesting phenomenon is that when, for example, a vehicle from this cluster to this one, when a vehicle travels from one cluster to another, they will actually carry the history of contributions from the other cluster. And that can actually make the model more reliable, of course, but it can also induce some communication overhead to transmit all this data. However, since this is all based on the same model, these models are highly compressible as well, which is another research aspect of federated learning. So, for this problem, we're considering a few independent test sets. We're considering 3 mobility data sets, which namely the Monaco, Luxembourg, and Cologne mobility data sets, which are real-world data sets, sumo-generated data sets for real-world scenarios. And we are considering also a baseline with the MNIST number recognition, which is usually used in such works for comparison. We have an open source implementation of this aggregation techniques, which can be accessed through GitHub and audited. So basically we have implemented our modified model, which includes a history of contributions, in which each contribution is hashed. So vehicles can exchange only the hashes of contributions that they have, which is a very low overhead operation compared to actually aggregating and transmitting the models. And the vehicles can keep the actual models in a compressed, ready to send upon contacts. This is just an example run. So basically, like I like I showed you in the fluxogram, federated learning is usually described in rounds, which is the number of times that you pass through the loop of training and distributing models. However, this is a little different because this is not round-based, this is very asynchronous. So since vehicles exchange their models upon contact, the X label is actually a counter of whenever a contact in the network happens and vehicles exchange their models, we perform the evaluation to check how the loss function is evolving over time in the network. So we can see that for a few minutes of the execution, this is actually converging like you would expect even for a traditional machine learning non-federated process. And our objective is to compare this with the federated learning rounds. However, this is a bit difficult because this is much more temporal. You can't assign labels to the rounds as they are kind of fuzzy. So we need to actually model how the communication aspects would affect the aggregation in traditional federated learning and in our model too. And this is what I am working on currently. So I have a few experiments. Experiment number 1 is basically considered a completely connected graph in which every vehicle can communicate with every vehicle, and they perform the opportunistic aggregation of models. In other words, they will be transmitting their models to every vehicle such that they all have the same contributions at the end. And this is the behavior that you saw in the previous slide. However, in a real network, this would be based on the vehicle mobility as they come into range with each other and they can communicate, and when they come into range with the network infrastructure. So the next step is to analyze how the model's contributions propagate through the network and how the loss converges. And finally, we need to test how the system is impacted by users with low quality data, or which actually intends to poison the model by providing random weights for the neural network, or just training with too few samples or bad quality data. And this is actually based on our previous work in which we are able to cluster the weights of neural networks contributed to federated learning in such a manner to find neural networks trained with similar data. In this case, with low quality data, they would stand out as an outlier in this process and could be thus detected and discarded in the aggregation process. And that is basically my work. Thank you.
Thank you. So as usual now, if you have any question for Lucas, now we have 10 minutes. And then after, since the third speaker is not here, we will end the session a bit earlier. So we will hear about Yann in the third day, in the last session. And then we will already be able to check in the hotel because the rooms are ready. So after the talk, we can directly go, and then we will have the coffee break. So now it's the time for the questions for Luca.
Yes.
Please.
Maybe I missed it because that was sort of the topic, but I mean, how do you decide when to update your model and do your macro? You don't have batches in the traditional sense, right?
Yeah, so it depends a lot on the data that the vehicle possesses. So basically the network decides on an architecture for the whole process, and every user needs to use the same architecture. And then they will have some time to train their model. And in our implementation, this is represented by a flag of when the vehicle has finished n number of epochs of training. And so when two vehicles meet, they can tell each other, okay, this flag is set true, so I have finished the training over the agreed upon number of epochs, and we can exchange data. So we assume that this is a high number of epochs such that the model can actually be properly fit. And then you just have to propagate all these changes through the network.
Okay, other question? Valerio?
couple of questions. One is that I don't know too much about the domain regarding vehicular networks. So the first question I have is, how are these links vehicle to vehicle? Are they large bandwidth, long latencies?
Yeah, that is actually very important. So we are considering for this work the SRC links. So of course there's limitations, especially in terms of context time and mobility for the vehicles, which will degrade the links to some extent and limit the amount of data. So we actually have a step before the actual process, which is the architecture search, in which you define how many layers and how many parameters actually describe the neural network architecture. And this is an optimization process, and we have some constraints regarding the link capacity. So you can define, for example, the maximum size of the model in terms of bytes, and how many parameters can be represented within these bytes for the process. So this has to be optimized in the design of the architecture based on the actual network conditions, and you can either model this or you can actually try to update this on the fly via measurements.
But in the real world, these links between
We consider LTE links and the SRC links for the peer-to-peer communication between the vehicles.
Okay. Then I had another question that is not connected to this one. Of Flight 11, I had the impression you were somehow, I probably missed it, but you were, it seems to assume that you will end up having all vehicles contributing. Is that the case?
Yeah, initially for proof of concept, yes. However, like I said, there are vehicles which can be... Federated learning is also heavily based on incentive. So everyone wants to receive a robust model, but no one wants to spend the computation to help train it. So this is a behavior that you have to consider in the network. In this algorithm, I consider this in a kind of simplistic manner as a vehicle only receiving the updates after their data has been validated via the clustering of their weights. However, when two vehicles meet, you have to decide a leader which can be fit to judge the other vehicle's data, the other vehicle's model, before they can receive the updated global model. This can be based on some reputation system, for example. So, in theory, vehicles that don't contribute meaningful data, they should not receive the updated model. So you have some incentive mechanism for vehicles to contribute.
It can be applied to many other things in
Yes,
general,
yeah.
in society. Okay, any other questions for Lucas? Yes, please.
Just to be sure that I understood, in your model you have the assumption that the number of vehicles which participate in computation are known and fixed during the computation?
Not exactly, because like I told you, the interactions sometimes are largely contained within certain clusters in the city. So it's possible that certain regions of the city have completely different models because there was no travel between them. However, when new entities arrive, or when two different clusters of vehicles communicate, then it's equivalent to introducing new participants in the network, and this strategy can still be applied of comparing the contributions of the model and exchanging the diffs of the contribution. So.
Okay, when you know that the computation is finished, you say on the other slide that continue until all
this is
then this condition 0.6
yes.
If you say all vehicles, that means you know how many vehicles should contribute.
This is basically just for the modeling. In theory, you don't know. You can observe the loss function over some validation data sets, and the vehicles can decide based on that. But in theory, it's the same flow in which you continue until convergence. and this convergence can happen within a cluster. However, when you introduce new data, this convergence will be disrupted for this new data and you have to restart the process.
Okay. Any other question for Lucas? Yes, please.
Could you come back to the algorithm
Yes. Back.
with the 6 points?
Yes, sure. This.
So about point 2, so each vehicle trains with local data. So that means the vehicle will train on the data that it sees, right?
Yes, exactly.
So it's like if you would be training a neural network with a batch with very similar data all of a sudden.
Yes.
Don't you have a risk of overfitting or giving bias to what is learned?
Yes, absolutely. And this is overcome actually in the actual aggregation process. Otherwise, each vehicle will train with their own data, and they have no exploratory data. So if they are ever in a new part of the city, in a new situation, they would be making wrong predictions. However, the different vehicles will be gathering data from different contexts and different locations. And when their models are aggregated, when they come into contact, then the model for both of them will be made more robust in the aggregation process. So they will exchange their weights and perform some aggregation, like averaging the weights one by one. And this actually converges into a model trained with the entirety of the data of the two vehicles.
You said you do experiment with MNIST?
Yeah. My experiments are run with mobility datasets. However, in the future, for publication, I plan to use the MNIST dataset, which is kind of the default for this problem. Yes.
So I really like this idea. It's a very cool idea. If I compare this to a classical distributed learning problem, so the real complexity or the real challenge here is it's mobility. Essentially, communication is following mobility patterns, right?
Yes, correct.
So is this a challenge or is it an advantage if you consider the application domain?
I would consider it more of an advantage because normally in traditional federated learning, you distribute the model and then at some point, let's say the average time that each vehicle takes to train a model, they will send it back to the network.
Server,
yeah. It could maybe cause some overhead, and it would at least slow down the process of convergence. And there's also the issue of participation, and scheduling, which is a big problem in federated learning. Like, you don't want every possible user to be doing this, otherwise you will cause heavy overheads in the network with the transmissions. However, if you can do this in an opportunistic manner, you are distributing this overhead upon each context time. And at the end, the overhead for the infrastructure is heavily diminished. So
you have some randomness and some natural clustering of the user then.
Yeah. And it actually also incorporates very interesting aspects such as the aggregation of IID data, which is identically distributed independent data across models.
Okay, and the second part of my question is then what kind of application domain do you see? Because it's really something I can imagine that some of the problems are related to the location of the user, or some data fed from cameras, or do you see some obvious application where this is really a fit?
So what is discussed the most in the literature is image classification and recognition, which will be a huge aspect of autonomous vehicles. They need to analyze camera sensor data. However, this is highly generalizable. So the experiments I'm running are running on mobility prediction networks. It is in theory generalizable for basically any AI task. And like it was asked for Eric, like these experiments are run on a recurrent neural network. So it fits different strategies and architectures in a satisfactory manner.
Okay, thank you. We have time for some more questions for Lucas. Okay, then maybe I have one. You know, so you said that basically with your vehicles that exchange data, they do some sort of diff in
Yes.
some sort of Git slang. You know, they check
Yeah.
what is the difference between their model history
Yeah.
and then what they don't have with each other. They exchange.
Yes.
Okay, then on a long term, we could imagine that this diff list grows.
Yes.
So in the long term, how do you have an idea of when to cut when the models become too old for being exchanged?
Yeah. So I see basically two approaches that you can take in this case. So what I actually used for this work is to have kind of a moving window of considering the last n contributions, like the last 20, and contributions older than that, you can actually aggregate and it kind of compress the contributions older than n into a single one.
Yeah, right. The question is, what do you think could be a good n? You know, from what depends from mobility, from other phenomena. How would you imagine how to tune this number of relevant models that could be worth exchanging?
There are many variables like the actual network capacity, so how many diffs can you actually send, as well as like the very domain of the problem. If it's data that tends to change over time, then that could offer you a threshold. However, this is something that needs to be optimized for the problem. It's hard to have a predefined value.
Yes. Okay. Well, I think we ran out of time. So again, thank you for your presentation. Now the session is over, so it's time to check in. So you can leave your luggage in your rooms, and then the coffee break should start at 3:30, but probably it's going to be ready a bit before that.
The first one is as a regular block device. So a block device is like when you have an SSD or something. Really, it's a basic block device in the Linux system, and it appears in /dev/pmm0. This is the way you would configure your NVMe to use it as a traditional SSD. So if you have this configuration, you have to format the memory, you have to mount it, and you have to use it as a regular device. But it can also be configured in another way, using something that is called direct access. Direct access is it's a mode where you can assure that no volatile caches are between your program writing something and the NVMe itself, because as the NVMe is really fast and persistent, having volatile caches in between is at the same time loss of time and loss of guarantees, because if your machine crashes in the middle of a transaction, you will lose everything in the volatile caches. So you can configure it as a direct access device, and in this case it is called /dev/tax 1.0, for example. And in this mode you cannot use it as a regular SSD. It is more like a device that you can memory map, and I will explain that later. And it gives you probably the most interesting guarantees that you can have with this new technology. So that's the mode everybody would like to use with this memory. So this is really recent, and in terms of use cases, we can, for example, use it as an SSD. So you format, you mount your SSD, and it works. And it's, as I showed before in the table, way faster than a traditional SSD. Then you can also use it as a direct access and memory map pool. So in this case, Linux is guaranteeing you that you can memory map some parts of this new memory inside your program address space. And for each transaction in this space, if you are using the right way, you can have very, very high guarantees of persistence. which is interesting because in general, when you are coding something and you have variables or data structures that are not written in a file in your disk or SSD, it is lost if you crash your program. But in this case, it would not, because that is the main point of NVMe. You can retrieve the data afterward. And it can also be used as a cheap way to have a high RAM capacity, because for many people that could be really interesting, like I'm thinking for when you have big data models that you want to train or something. In this case, you have to configure the BIOS of your machine to extend the RAM memory that you have with the NVMe. So as it is slower, Linux is doing something clever with these two memories. It keeps the hot pages in the classical DRAM, which is faster, and pushes the coldest pages in the NVMe. Now, what is RDMA? So this is another technology, completely different, which is a network protocol that you can use to access distant RAM in another machine. It is already used a lot in big data centers, mainly, and it is not using the CPU, which means it's the network card that is directly accessing the memory of the machine without asking permission to the CPU to give the data. And it has a very high bandwidth and low latencies, which is always good to take. Now, in general, RDMA is used when an application has to make big transfers or have very low latencies. So that would make sense for distributed calculation or, many big usage today. So the question you could ask is, why would we want to use NVMe and RDMA at the same time? I personally think that these two technologies have many common points that we could merge together to have something new, a new brick of software and a new interaction with the hardware. And first, we have to talk about the NVMe limitations, because I started by explaining why it's wonderful, but it has limitations. The first limitation, and maybe the most interesting one, is that it is only compatible with some really high-end CPU from Intel. So it's a really private technology, and you cannot use the module I showed you before in any machine you have. You have to get the right machine with the right main board and the main CPU from Intel. So that's a problem, because we would like to use this technology in many other cases when you have, I don't know, maybe small devices or AMD technologies, or I don't know. It has a limited bandwidth compared with DRAM, so that's something to take in consideration all the time. It's supposed to look like RAM, but it's still like 10 times slower. It's not that much, 10 times, but it is. Now it requires to use specific libraries and CPU instructions, because as I said before, you can have really high guarantees, but it comes at a cost in terms of development. You have to ensure every transaction is safe and make sure if a crash occurs, you won't have a weird state when you recover the data, all this stuff. Now, for hyperconverged infrastructures, so I don't know if you know about hyperconverged infrastructures, but the idea is if you have a big enough cluster, you can say, okay, I will have one rack of machines dedicated to CPUs, one rack of machines dedicated to disks, memories, one dedicated to RAM, and then you combine them together to give virtual machines to the users. So this is a really interesting way to share the resources. And my question is, what about shared NVMe? Because this is not really available right now, and it could become interesting in the future, I guess. So this is one question I'm trying to answer. Now, today, can we use NVMe and LGMA together? At first, we could say yes, because Intel gives us a library that is called librpma that is meant to use both at the same time. So you can interact with a distant non-volatile memory module through RDMA, but no, you have to adapt your code again, and we're too lazy for that. I don't know for you, but I'm too lazy for that. So I don't want to remake every code I have that works on one machine with NVMe and adapt it to use this weird library to make it work. I would like to have the same application on another machine and virtually have an NVMe device on the other machine. But maybe it could become a reality because there is a new improvement in the Linux kernel that is allowing us to share devices, and I will talk about that a little bit more. And so my very scientific conclusion now is it depends, because it depends on how lazy you are and how much guarantees you want. Now this is what I'm trying to understand and work on these days. It is called RTRS RNBD, and these are kernel modules that have been added in the latest versions of the kernel. These are designed to share a block device through RDMA. So if you, for example, have an SSD that you want to share with another machine, and these two machines are linked together through RDMA, you can set up these two modules to make the client machine see a new /dev device that is in fact in another machine, a distant machine, a server machine. And this is exactly what we would like to have for persistent memory, for NVMe. Because if we could have this kind of behavior, there is no need anymore to rewrite the programs we had that work on a machine with NVMe. So now, this is how I understand the behavior of RTRS and RNBD today. If you have a client that is running a software that wants to write in a distant NVMe module, you have to go through all these paths. And the problem is, as always when you're working with NVMe, you have caches in between. And these caches are a threat to our guarantees, because if something crashes between the client or on the server or even the network, you can lose data because it was in volatile caches. It was not yet persisted somewhere. And so you cannot give the guarantees that a program is supposed to give to NVMe in normal conditions. So the idea we would like to code would be to give an equivalent of the direct access feature that I was talking about before, that allows you to bypass all of these caches. So it's a simplification because hardware caches are not that easy to bypass. You have to modify the code you're running. But for software caches, at least, you can disable them in the OS. So that would be an interesting way to have as direct as possible access to a distant NVMe. And so we would like to code something like that to see what guarantees we could have in this case. So the next steps of our contributions, we want to have something equivalent to direct access guarantees when we work with remote NVMe, because it is easy to share NVMe module when it is used as an SSD. That thing is easy, but as soon as you require to have the guarantees given by direct access, it's impossible. It's not coded yet in the two modules I'm talking about, and the only way is to use the specific library of Intel, and this is, at least to me, a problem. We have to make it easy to use as RNBD, so the idea of having a virtual device on another machine sending the traffic through RDMA is, in my opinion, a really elegant way to solve this problem. And we would like to add in-network features. So I'm not talking a lot about this because that's the next presentation with Sebastien. But conclusion, there is a lot of work remaining because all of I said is only ideas for the moment. We know where we could go, but it's a hard path, and so let's hack the Linux kernel.
Thank you. Questions? Yes.
Can you just go back to slide 15? I was a little bit confused about the cache structure here. Maybe you can
really oversimplify it.
Yeah, in particular, the left-hand side, the hardware cache is on top of the software.
Yeah, but I mean, if you are using, let's imagine you have NVMe here instead of the network interface. That's the path you would have in your machine because you have program running on CPU. And when you try to write something, everything, a variable or anything else, it will first go to hardware caches inside the CPU, then eventually go back in a software cache from Linux that is giving you caches in the RAM, and then at the end you will maybe go back to hardware caches and then go to a persistent system. So that's really problematic for us.
And on the right hand side?
And the right, so it's kind of the same, but in these cases, the hardware cache is not in the CPU because the CPU is not called when you are writing in RDMA, but it is in fact something that is inside the network card receiving the data. So there are buffers inside this card, and I know, for example, in the a very interesting thing I discovered.
So these are different hardware caches.
What?
These are different hardware caches. That means the one on the left hand side.
Yes,
and the right
it's
hand
not
side.
exactly the same. It's the same principle because they are volatile. They don't have any guarantees for us, but it's not the same.
One
caches.
is attached to the CPU and the other is to the
Yep, exactly. And it's easier to solve this problem with a CPU than with a network card.
Other questions?
In terms of time scale, can you say, okay, CPU it takes so much time, hardware so much time, and then how much time to?
Yeah, it's hard to answer because it really depends on the infrastructure you have. But let's imagine the longest time would probably be here in the network, but even.
But the
here, it's
real
microseconds.
numbers, like
I don't
because
have
I don't even know if it's microsecond or nanosecond or millisecond or.
Here, this connection, which is the slowest in my opinion, is microseconds.
Okay.
The order of microseconds, and depends on what you have as an RDMA network. For sure.
It's there you have your 40 gigabits or.
What?
The
bandwidth.
You said. I remember the 40 or 400 gigabit per second. It's
you can
on that link.
Yeah, you can go that fast if you have money. But we have 100 at the university. That's already a lot to test.
And then on the other.
In between,
the other blocks,
this can go to nanoseconds or even
it's
slower.
nanoseconds
So
only.
For sure, but the interesting thing is here, in general, when you are using a CPU to write into NVMe, as you have to trigger some low-level fancies and stuff to ensure the guarantees you want, you will lose a lot of time too, and sometimes it couldn't go to microseconds too. So that's why it makes sense.
Especially software, I was just wondering if it's possible.
If it's possible.
In software, is it possible to be faster than hardware?
Oh. Yeah, right here I have no idea. No, in general it's not. That's why we want to bypass these caches also. Because in a traditional machine, when you have NVMe and you are trying to write to it, having stages of software caches in the middle, it's a complete loss of time because you are copying twice the same thing, and you will have like I don't know, for instance, 5 microseconds and 10 microseconds. So why do we bother about the first one? We can write directly to the. That's also the meaning of direct access. Yes.
You mentioned once or twice. It needs the Euro protein needs high-end Intel CPUs. It needs Intel libraries and so on. So does that mean all these mechanisms you have described, they are how they depend? They depend on.
Yes.
That it's not possible to use anything.
It's
or to transfer.
It's really no, it's not really possible because, for instance, you won't have the compatibility even in hardware on the motherboard to put the new modules in other machines. If you have an AMD machine, for example, you cannot use the NVMe module. it won't be recognized at all, and it uses new instructions in the CPU to communicate with this module because it has many new features. So that's why it's so hard, and of course Intel is not really ready to open their way to work, of course. Yep.
So now there are more and more, there are faster and faster non-volatile memory. In the end, there will be just one non-volatile memory.
Yeah, maybe.
And then
but
instruction of RAM and solid memory.
You mean non-volatile memory could replace our volatile memory?
Yeah, why would you need a volatile memory if you can do everything as fast?
That's a really good question, but to me, volatile, the volatile behavior of our actual RAM today, it's not something on purpose. It's a limitation of the hardware we had when we tried to make computers at the beginning. So yeah, it makes sense to think that one day maybe we will have non-volatile memory everywhere. That could make sense, but it's not here at all. And for the moment, the challenge is more how can we add the features of NVMe into the machines we have developed, because every software will have to be rethinked to work with this new behavior. That's really different from what we did before.
Yeah.
But yes, you could maybe put your laptop in just the time needed for the electrons to go everywhere. Nice.
Yeah, I have a question. What I'm trying to discern, by the way, it's great. I've been working before, and the non-volatile memory was the girl everybody knows about, but nobody have seen.
Yeah.
So I'm very happy to see it. But
concrete application.
What I'm trying to discern is, are you doing something that could be emulated by other ways? Your work. If I can emulate what you describe with software, then I will have worse performances, and then you're trying to improve these performances. But if I can't emulate, then you're really enabling something. What would you?
You can't emulate these kind of performances, I think, because you could, but you would lose some guarantees in the way.
So your work, the work that you are describing, is really to improve performances that otherwise would be very bad if you had to emulate with the software.
Yeah, you cannot really emulate with the software the persistence, for instance. That's something you need a hard drive to do.
But that's my question, and this is my whether you're trying to enable something that is not possible by other ways.
Yeah, I think. I think this is not possible the other way. You cannot have these performances and these guarantees at the same time.
Okay. Merci.
Merci.
So we are staying on the topic, if I got it?
Yeah.
Yes, second half.
All right. The floor is yours.
Thank you. So, welcome. So I'm Sebastien Vaucher and the University of Neuchatel, and today I'm going to present RDMA Better, Faster, Stronger. So, you've heard about this RDMA technology just before, and well, what it does is you can access memory directly without involving the CPU. And in terms of protocols, there exists mainly two that are widely available on network cards you can buy today, which are iWarp and InfiniBand. And because of the cards we have, we use Rocky. So ROC is pronounced Rocky for some reason. And that's basically InfiniBand transported over Ethernet. And that's the protocol we will be focused on in this work. So this, you've heard about NVMM. So basically it's halfway across RAM and SSD. And when you do RDMA to best persistent memory, we call that RPMA. And there are two problems we want to solve. Well, more problems, but mainly problems with RDMA on one side and problems with NVMM on the other side. So the problems with the RDMA is mostly that it's intended only as point-to-point. You have a server, you have a client, and that's it. You cannot have one client. Well, you can have one client talking to two servers, but that's actually two connections. They are completely separate. And with NVMM, there are some problems. So as we said, you can only have it on a very specific Intel hardware. Also, it's slower than RAM for the moment, and it has no built-in redundancy mechanism. So for now, there are no RAID controllers for NVMM. And we want to provide a solution to those two problems using in-network programmable switches, which is the Tofunmi switch. So we want to have a point-to-multipoint RDMA, and using that, then we can disaggregate NVMM using RDMAs like Remi just presented. So this Intel Tofunmi switch, which was acquired from Barefoot Networks 2 years ago, I think, is a fully programmable switch ASIC, and that you can program with the P4 language. So it's basically a switch, so it's same as a normal switch, except when you buy it, it's just a rock, it knows nothing. You have to tell it what to do with network packets. And it's very interesting in that whenever your P4 program compiles, that means it runs at line speed. So we have the Tofunmi one, so that means whenever I write a P4 program and it compiles, that means the program can handle 6.5 terabits per second of network packets. And it works basically in stages. It's a pipelined architecture, and that's basically how it works. So the goals of the project is to make NVMM and RDMA better, so that is disaggregated through the network. So that is, you can have your client somewhere, your server somewhere else, but they don't know where each other. Well, maybe it's like they are abstracted, let's say. The client does not know where the servers are, and the servers don't need to know the specifics of the client. We want to make it faster by scaling out and using multiple servers for memory operations. And using the Tofunmi switch, we can do that very fast. And we want to make it stronger by replicating across multiple servers, also while keeping the other points. So points to multipoint, what we want to do. So we have our switch somewhere in the network, and we want to provide to the clients the illusion that the switch is actually the server, but that contains the NVMM. And for the servers, we want to provide them the illusion that there is only one connection going to them. And well, basically what it is, it's a man-in-the-middle interception that we do. We take the network packets, we see what is in there, take the values, the keys, and replace them with other values so that everyone is happy and has the values they expect. And that allows us to have one client talking to multiple servers with only one connection. So the Rocky protocol, how it works. So in practice, it's just InfiniBand over UDP. And when you do read and write operations in the InfiniBand with the RDMA protocol, there are a few fields that are a bit tricky to emulate. So basically, this is the core of the problem that we have to solve. How to replace the values in those fields with values that make the machines happy. So for instance, you have the Q pair number, that's to identify a network flow. You have this packet sequence number that they use to know the order of the packets. So for instance, when you have one client talking to multiple servers, you have to make sure that this counter is incremented for each machine individually. And we keep state across all the machines. When you have an operation that spans multiple packets, so that your read or write operation is longer than the MTU, the packet is split in only first, middle, and last packets. So if you have only one packet, it's only. If you have two, you have one first, one last, and otherwise you have a first, as many middle as you want, and the last. And one thing that is important, or that is critical for the Tofino switch, is that we have to use stateful operations, because only the only and first type of packets have these values. So the key is very important, is what provides some security to the protocol. In order for, if you have your RDMA server somewhere on the network, there's not someone that can just send arbitrary packets and write to your RAM somewhere. So this is only in one packet, so we have to remember it to emulate later the whatever type of packet we need to craft. You have this virtual address concept, so you have the whenever the network card initiates an RDMA connection, the server provides a virtual address space to use, and each machine basically has its range of virtual addresses that then match to somewhere in physical memory. And DMA length, that's pretty self-explanatory, is like the length of the read or the length of the whole write operation. So what we want to do to go faster is to stripe the write and reads open. So if we take like the throughput of NVMM is about 3 gigabytes per second, more or less. And the network throughput we have with our 100 gigabit switch is 12.5 gigabytes per second. So that means we can easily make NVMM go faster by using multiple servers and scaling out through the network. The network won't be a bottleneck. So basically what we do is, for instance, here we have even addresses go on one server and odd addresses on the other. And because they are striped, you only wait for every other packet. So you can go more or less twice as fast. That seems really easy, right? No, it's not. Because, for instance, here we have the address space on the client. That one we can actually control, because the initialization packet in the Rocky protocol, they allow us they allow the server to tell the client what the address space is, and we just tell our control plane that runs on Tofino that the address space of the client starts at 0. That is, we simplify our computations a bit. But on the real servers, we have to use the real addresses. And also, we don't want to, like here, we don't want to have a gap of between every other address that we use. Otherwise, you have to buy twice as much NVMe for nothing. So we want them to be continuous. So still, right? It's just some war on indexes. Nope. Because when you program with P4, especially in the Tofino platforms, you cannot have loops, you have no division operation, you have no modulo, you have a limited pipeline length, so there's some number of operations you can do before compiler refuses to compile. There are some data alignment constraints. So, for instance, if you want to just shift bits in memory, you have to do it in a certain way, otherwise you cannot. And when you want to do stateful operations, you are limited to one simple read, modify, write operation per stateful memory. So with all of this, the computation becomes quite complex to code, actually. So let's take an example of how that would work and how we would modify network packets. So let's say the client wants to write 12 kilobytes of data. So that's if you have an MTU that is a bit bigger than 4K, so that everything is aligned, that makes 3 packets. You have a first, a middle, and a last. And in the first, we have this R key, which is this security because it's just a value. There's no cryptography involved or anything. We have the zero-based address of that set that we control. We say the length, and then we have this PSN, so the packet sequence number. We have to take the previous one, so of the packet that would be just before that one sent. And then we have +1, +2, +3. So if we want to write that to 2 servers in a striped fashion, that we will transform the first packet goes as a first to the first server, the second goes as an only on the second server, and the last goes as the last on the first server. So that from the client perspective, it's still coherent. You have first, middle, last, and for each server they see either first, last, or just only. So for them it's like always one operation. So every server thinks that there is only one client, and the client only thinks that it talks to one server. Let's see what we should modify. So in the first packet, the R key we have to modify it because we have to use it the one of server 0 and not the one that we created. We have to compute a new address offset to comply with the new, the virtual address space of the server and not of the client. The length is different because this we only have 2 packets now instead of 3. And the PSN, we have to take the PSN of the last packet we sent to server 0 + 1. It's the same, a bit similar here, except that we don't change things. We have to also add things that are not in the original packet. So for instance, we have to add the R key of server 1, which was not there before. We have to add the virtual address space relative to server 1 and then align everything so that it fits. The length is now different, and the PSN same as the server 0, but for server 1. And the last packet, also we have to take the previous PSN of server 0 +2, while the original has a +3. And as you can see, we need to change every single field of every packet that crosses our switch for the abstraction to just work. And most computations are stateful. And when you program in P4,
rarely want things to be stateful. It makes everything much harder to program. So that in P4 it's actually quite hard to perform those modifications that seem quite simple at first glance. And for read packets it's even more complicated because you have only one query and then you have multiple packets for the answer if you want to.
But it works so well that people could take Tofino and use what you're proposing.
Oh yeah, that would be like the best case scenario. Someone takes it and just runs it on their Tofino. I guess that's also one good point of the Tofino is that you buy it without the software basically. So you can, like you buy a PC and you run whatever you want on it. If you want to download whatever software from GitHub and compile it on your machine, you can. So maybe with the Tofino, there will be at some point, I don't know, some kind of repository of P4 programs that are useful. Maybe. I guess, yeah. If we manage to do it on the Tofino, to me, there's no incentive for someone to make a hard-coded switch, like a physical switch for that. Especially since the Tofino is no slower than on another switch.
Yeah, but it's more expensive.
Not that much.
No? Oh, okay.
Not that much.
Yes.
So you are now been using Tofino for at least 1 year, right? So if there was one feature that you could ask Intel to implement to make your life 90% simpler, what would you be? What would you do?
Oof, that's I don't know. I mean, it has everything we need. You just have to always think about what you want. That's the point. The point.
So it should help you in thinking.
Or maybe, yeah, I guess the improvements in the compiler eventually, so that it does some of the hardware-related thinking for you. It does, but not. It depends. Sometimes it does, sometimes it does not, and you have to always think about the limitations when you program on it. I mean, not simple stuff. Simple stuff is trivial.
Nothing, one single thing that is very specific.
No, I don't think I have one thing in mind.
Yes. So last question.
So you said that you have some sort of state in the switch because the address markings stay on the switch. Is that correct?
Yes.
So where are they, like? What type of memory are you using? Is it scalable, like in the sense that if I have a data center, I have like I don't know how many terabytes or whatever of memory, I have to address all of these, and I have like many clients, many servers, and I'm keeping different markings for each one. How
well, so the stateful memory in Tofino, they call that registers. They are basically arrays. But the limitation is that for any register, you can only do one read, modify, write operation per packet. So if you can have like I don't know, some dozen of operations in total, not more. So even if you had many terabytes of this, which you don't have, it's more in the order of mega, not tera.
No, but I meant the tera, I meant the space that you are addressing. So you're addressing this modules that he just showed. No, that's like.
Ah, you mean okay, yeah, the NVMe address space.
Yeah.
So yeah, no, that's this. You don't need much because you only need to know the first address basically and the length.
So it's just one for each client and times the server. That's not so much.
Yeah, it's not a lot of memory because at some point also we want to go up to 4, maybe 8 servers because more we don't see the point. And at some point you also reach the 100 gigabits per second limitation, or then you have to do aggregation, and we don't want that. So it's not that much memory to store the address spaces. What you have to do is more to have for each connection know the offsets of every server to then be able to compute. But because the Tofino has so That's the limitations on what you can compute. You have to make sure that you store them in a way that allows you to do what you want to compute, basically. Does that make sense?
I understand, yes.
Okay. Thank you.
Thank you.
Can I say something? Yes, yes.
No,
you can.
No?
I changed my mind.
Does everybody has written about the menu tonight? Did everybody write their own preference on the menu? Okay, so that's fine. So you should just put the cross on any choice of the about tonight. Okay, just collect it.
So welcome to Peterson.
Hello everyone, my name is Peterson Yuhala and I'm a third-year PhD student at the University of Neuchatel, and I'm representing to you my work on Intel SGX shielding for GraalVM native images. Now, the popularity of the Java programming language has led to its wide adoption in cloud computing infrastructure. So we can see various popular frameworks like Hadoop, Zookeeper, and Spark are all based on Java. Now, the use of these frameworks have raised security and privacy issues because we have users sending possibly sensitive data to untrusted cloud infrastructures. So to solve this security issue, processor vendors introduced trusted execution environments, or TEs, like Intel SGX, which provide secure enclaves where you can run sensitive data on code at runtime. However, the complexity of TEs has hindered their adoption by developers, and this is because programming TEs is usually done in very low-level languages like C and C++, and it's difficult for programmers to integrate their TEs in programs written in higher-level languages like Java. So to solve this issue, several research works propose library operating systems like Graphene SGX, which permit to run unmodified applications inside the SGX enclaves. Now, this approach works, however, it leads to a large trusted computing base, which essentially lowers the security and performance of the application. Now, the solution to this is to partition the application into two parts, that is, an entrusted part which runs out of the enclave and a trusted part that runs inside the enclave. Now, the partitioning process is it's more or less simple for programs written in procedural languages like C, but it becomes very complicated for programs written in managed languages like Java because we have to ensure efficient cross-object or inter-object communication across the partition components, as well as consistent garbage collection. So in order to solve this problem, we developed a framework to partition Java applications, and our partitioning approach is based on annotating Java classes as trusted or untrusted, and so for the trusted classes we keep them inside the enclave, while the untrusted classes we keep them out of the enclave. Now, based on these annotations, we perform bytecode transformations on the classes. So for the trusted component, we replace all the untrusted classes with proxy classes, while for the untrusted component, we replace all the secure or the trusted classes with proxy classes. And at runtime, the proxies perform enclave transitions to the opposite runtime. So after we do this, we then use the modified classes to build native images using GraalVM. GraalVM is an efficient multi-language JVM implementation by Oracle, which permits to ahead of time compile Java applications into executable binaries called native images. And native images do not require a regular JVM to run at runtime. So what we have is, at runtime, if we instantiate a secure object, for example, in the untrusted runtime, that's going to create a proxy object which will then perform a transition into the enclave to create a corresponding object which we call a mirror object, that is like a mirror copy of the proxy object. And the same thing happens in the opposite direction. So if we create an untrusted object in the enclave at runtime, it's going to instantiate a proxy object which will perform a transition to the opposite runtime, that is the untrusted runtime, and create a corresponding object which we call the mirror object. And also, each time the method of a proxy object is called, it simply performs a transition into the opposite runtime and calls the method on the corresponding mirror object. Now, this one problem with this approach is garbage collection, because we need to ensure that we don't destroy our mirror objects before the proxy objects, and we need to make sure that each time we destroy a proxy object, we have to make the corresponding mirror object eligible for garbage collection. So we solve this problem using weak references. So at runtime, each time we instantiate a proxy object in any of the runtimes, we store a weak reference to the proxy object in a list. And we also store a correspondence between the mirror object and the corresponding proxy ID in the global registry. So we have garbage collection threads that run periodically at runtime and scan the list of weak references. And each time a null reference of a proxy object is found, this means the proxy object has been garbage collected or is eligible for garbage collection. And so this performs a transition into the opposite runtime, which then removes the corresponding mirror object from the global registry, and this automatically makes this mirror object eligible for garbage collection if it is not strongly referenced somewhere else in the program. So we evaluated our framework with two macro benchmarks. The first is PowerDB. PowerDB is a key value store developed by LinkedIn, and GraphQL is a popular graph processing framework. So for PowerDB, we have two principal classes. So we have a reader class and a writer class. So we partition the PowerDB using two scenarios. In the first scenario, we have the reader class inside the enclave and the writer class out of the enclave. And in the second scenario, we have the reader class out of the enclave, while we have the writer class inside the enclave. And so we observe that the performance of the partitioned versions, that's for both partitioned scenarios, is better when compared to the entire application running inside the enclave. So similarly for GraphQL, we partitioned it in such a way that we have the graph shader out of the enclave. The graph shader is simply a class that breaks down the graph into multiple components. And we have the main graph processing engine class inside the enclave. So after partitioning, we observe that the performance of the partitioned version is better when compared to the full application running inside the enclave. So in conclusion, our framework leverages Java annotations and bytecode transformations for partitioning Java applications, and we leverage a mechanism similar to remote method invocations to ensure proper object communication across both partitions, and also to ensure consistent garbage collection. So just as an aside, we received a notification of acceptance for our work this morning from middleware. So thank you for your kind attention, and I look forward to your questions. Thank you.
You're supposed to talk for 5 more minutes, please. No, I'm sorry.
So this will leave more time for having a drink because he got the paper accepted.
Do you have any questions? Can you show me the schematics of all the flow of the
framework?
Yeah, this one. But this is a very basic question from my part. I'm not an expert. So the Java class, I know very well Java, but gets transformed into some machine level compiled code in Hadoop.
Yeah, because normally with Java, the Java code runs in that is normal. It runs in the JVM. That is, we have the classes that are compiled first of all to bytecode, and at runtime the classes are interpreted or just-in-time compiled by the just-in-time compiler.
Yes.
However, with GraalVM, it permits to ahead of time compile the applications, the Java applications, to executable binaries directly, so they don't run inside the JVM at runtime.
Very interesting. But this is not a feature of Hadoop, so it's orthogonal to Hadoop or to Spark or...
No, it's not a feature of Hadoop. We just use Hadoop as examples to show that Java is popular framework used in cloud infrastructures, and hence the reason why we focus on Java to work on it.
So actually, Grand VM is the new, let's say, research fork of the VM from Oracle, and they support multiple languages.
Ah. Yeah, sounds good.
It's really something great, actually.
Why not earlier? Sounds. Anyone else?
I actually have a question, but it's very speculative. I don't know if it makes sense at all. So you have shown this process of going from. I was involved in this work, so I know it, but I'm asking something to Peterson, especially for this. So we take Java classes, so we compile all of them down to everything that goes inside enclave and something.
Yeah.
So how about the reverse process? Is that possible at all? Let's say I give you some binary, I give you two binaries, and you can, let's say, do the reverse process to say, I don't give you that Java, but I give you Ruby annotation, or something that is in another language.
So you want to translate from machine code to Ruby code, from your Java code. I mean, it will be.
It has been done in the past a lot.
I think anyway, I've never tried that, but I think it's going to be a bit complicated because we have different languages that are compiled to machine code. You have, let's say, your Java code in this case is compiled to machine code. You have C code, C++ code that is compiled to machine code. So how? And when you get to the machine code level, I don't think there is any indication of the higher level language that led to that machine code.
I know. I'm telling you, you get to choose. Say, is it possible for a decompiler to take whatever you have as a result and decompile back to Python or Ruby or whatever?
I think the idea with the decompiler is that when GraalVM compiles your classes to machine code, sometimes it does speculations, and those speculations may or may not be right. So at runtime, if it realizes that those speculations were wrong, it then does a decompilation, that is a reverse process of compilation, and it does not change it back to Java code. It simply undoes the speculative compilation that it did before in order to correct the mistake it did before. I don't think it's anyway. I've never tried it. I don't think it's feasible to translate from machine code back to the original high-level language code. Anyway, but what is the purpose, for example, of doing that?
You have you have a team of Java developers. All of them are fired, and now you have a new team of Python developers. You give them.
So you want to do reverse engineering. You want to
rather than having to implement everything.
That would be very complicated.
That's a reverse Babel situation. You reverse the Babel Tower problem. I have a question on your performance graph. So if I get it correctly, so the baseline, the first one. So the baseline is the
entire application running inside the enclave. So after partitioning the application, we reduce the amount of code in the enclave. And this essentially, so there are two things. It first of all increases the security, because when you have a large trusted computing base, by default, well, I can say a larger trusted computing base implies lesser security guarantees. The more you have code in enclave, the less security you have.
Right. So the red case here is the lowest security, and this is by why it's the fastest.
Well, in this case, we're not. I had two points to make. I had to speak about security first, then performance. In this case, we show just performance, not the security.
Yeah, I get that. I get. So obviously, the fastest is the lowest security. And what you're showing here is that.
Yeah, exactly. The fastest is the lowest security because it executes entirely out of the enclave.
Mm-hmm.
Yeah. So that's where we have no HX. So no HX is the red line there. We don't have any code inside the enclave, because each time you put code in the enclave, it decreases the performance because you have enclave transitions that are very expensive. Each time you have code in enclave that needs to perform system calls, for example, to do transitions.
And so what you're showing here is that by making shrewd partitioning, you can get almost the same performance, but with the security.
Yeah, that is by choosing just a portion you want to secure instead of putting all the full code in there, because you have systems to simply throw everything into the enclave and run it, so without doing any work to partition. So it's difficult for users or developers to manually partition their code. So we developed a framework that does it automatically. You just indicate which classes you want in the enclave and which classes you want out of the enclave, and it does the partition for you.
Okay. Yeah. Thank you. Okay, Andrea, I guess. No, there is one more.
I have a bit of a side question, but what is the speed up of using a Java program in GraalVM and without?
I don't have the numbers off head, but there are some papers I can refer you to, where you can get all the information. So I can send it to you after. I don't have it here.
All right. So thanks, Peterson again, and.
So welcome to this second day of the summer school. We have the first session of the day, which is on network systems, and the first speaker is Panos. He's actually doing his PhD under the co-supervision of both Josef and Valerio. He's in Zurich, but he's immatriculated in Neuchatel, so he's coming from time to time. And he will talk about leveraging decentralized data quality control to track quality issues in metrics observation.
Okay, so hello everyone. I'm Panagiotis Gkikopoulos, and I'm going to talk a bit about using decentralized data quality control as a way to improve the quality in data that comes from metric observations. So I'm going to start by introducing the data-driven systems that we envision this work to enrich. I will mention some of the challenges that we have encountered when we try to do this kind of data acquisition. Then I will introduce our concept of reproducible data acquisition and quality control. Present our case study, which is to control quality metrics on microservice artifacts. And then I will move on with basically presenting our solution and the current results we have. So when we talk about data-driven systems, we mean any system that is basically deriving some of its decision-making logic from data that is collected automatically. And in some cases, the data that is obtained may actually not be fully deterministic, or there might be unforeseen issues when collecting a large amount of data over a large period of time. Systems like that could be driven by rules or policy engines, for example, when blocking cloud environment deployments because they have too many security issues. There might be just generic custom scripted business logic, but also it might also be input data for AI systems. So some of the challenges that come up when we talk about data acquisition in these cases are basically the result of multiple issues such as equipment failure or network issues, and this can basically either lead to data being missing or data being corrupted. And this is only for the local use case. When we talk about the distributed acquisition, as we'll see further, there are additional problems that come up. So these are some of the challenges that we want to tackle. Our concept from this is to use reproducible data and also data quality assurance. So essentially, we want to use quality assurance methodology in an automated way to enhance data that we acquire reproducibly. So this means basically we have a data acquisition workflow, and we reproduce it across multiple systems, and we want to verify that they all arrive at the same conclusions. And this is something that has not been done in an automated way yet, and this is something that the Emerging Interest Group on Reproducibility by ACM has called a wish-listed feature for future tools to enhance reproducibility as well. So the use case that kind of motivated us at first was what we call the Microservice Artifact Observatory, which is essentially an informal collaborative effort to monitor the evolution of microservice artifacts. Those can be Docker containers, Helm charts, serverless application specifications, and whatever else. And basically, what we already had before I started my PhD was collection of data sets and custom data crawlers that were collecting data from these repositories. And this is basically an overview map of the type of quality metrics we were collecting specifically on microservices. So it might be marketplace metadata, it might be static quality checks such as code analysis or specification analysis, or some more dynamic checks such as benchmarking and monitoring them at runtime. Just to further elaborate on this, an example that we worked on extensively over the last year was basically monitoring Docker Hub and collecting some metrics on hardware compatibility. And this was further augmented by some custom analysis that we did because the public metadata doesn't give us enough information. But that is just to illustrate the example. And in order to do that, we monitored for a very long amount of time. So naturally, we ran across all kinds of issues. And I've basically categorized them in a rough way into local and distributed. So we were using multiple nodes for a certain amount of redundancy in order to make these observations. And some problems were localized and resulted in data loss, and some problems were not. So when we talk about local problems, we mean that a certain node has trouble doing its work. So it might have a hardware failure, it might have a network failure, or it might encounter a rate limit in the case of web crawlers and API crawlers. And when we're talking about distributed observations, we might have the problem of diverging data on the different nodes, whether that be that they are not synchronized properly, whether that be one node is here and the other one is in South America, for example. And in some cases, the results of certain experiments might be non-deterministic. So they might run an experiment that will not always produce the exact same output. So we need to figure out some way to get all of these to agree and to compile the data set. So with that, we arrive at our research questions, which is basically what are the best strategies for us to be able to pool this data and also produce a better quality, basically a data set that is better than just the sum of its parts, just getting all of the redundant observations together. How do we evaluate the improvement that we are producing in terms of the quality of the final data set, and also how are we going to structure this in a way that it will be useful when integrated into autonomic systems. And here I just have some pictures as examples of data-driven systems, for example, traffic control systems based on IoT devices, and also automatic cloud deployments. So the method as we propose it is basically a decentralized form of data quality and quality assurance. So the idea is that we have multiple nodes that are effectively running the same data acquisition and contributing data in parallel, and then afterwards we can pull the data and cross-validate it among the different nodes, which is basically the main contribution in this case. So this grants us the advantage that if we have any failures, we can use the redundancy that we have to fill in the gaps, but also we can resolve any conflicts that might be caused by data corruption or diverging measurements. And in this particular case, because we're talking about a decentralized system that is operated by different entities, we also have the added trust that this is being at least semi-independently verified and reproduced. And also that our system, of course, does not have a single point of failure in this case. So our design is based on a geo-distributed system. Though, of course, at this stage, this is mostly theoretical because, yes, we have 2 nodes in Winterthur running on the same infrastructure, so not really distributed in that part, and 1 test node in Argentina that is not fully operational yet, and hopefully very soon also a node in Neuchatel. So again, the idea here is to have independent reproductions of our experiments, and so independent verification, and also to achieve this loose coupling that prevents us from having a single point of failure of the whole system. So each node, which corresponds to a collaborator in this case, is basically comprised of our own orchestration system, which is basically the glue that holds our architecture together, and it's this whole automation control, which is basically the software that will run on each node. We also use a shared registry among all of the nodes so that they can report on each other's activity, and that is basically the only direct channel of communication between the different nodes. So they are not exchanging data directly outside of the verification step, and they are also not able to dictate to each other what they're supposed to be doing, so they can only opt into experiments. And then we have the individual tools, which is exactly what we're trying to reproduce and what we're trying to verify. And the idea being that an existing tool that somebody has is easy to integrate into our system and be used with this whole architecture. So the way data acquisition works at this point is basically a collaborator is registering a tool with us and associates it with a dataset they want to create, and then they can activate that on their own node, and it basically manages, in our case, though this is an implementation detail, it manages some Git branches to make sure that every node has its own branch, and then we run the tools periodically. And then other nodes can also opt into this and also schedule the same experiment so they can run it in parallel. Which then brings us to the dynamic cross-validation. So we have multiple nodes giving us data. The idea is then how are we going to make sure that they agree. And here there are multiple ways to do this, but we have basically decided to use group consensus for this, and for some values and aggregation for some others, and I will explain the selection a bit later. And then we also want to do some outlier analysis to help clean up the data a bit. Basically, to select the data, we want to collect all of the copies of the dataset, and then we detect entries to the data that was, that of course exists in the majority of the nodes. And once we have that, we can resolve the conflicts. In the case where a particular data entry is not submitted by at least more than half the nodes, then it gets rejected because we cannot establish a majority in this case. So to resolve the conflicts, we basically have we're basically evaluating with 3 methods, which initially were mapped to the type of data, but afterwards we wanted to do it selectively. So the person who is designing the dataset can tell us which conflict resolution method to use. We can use majority, we can use aggregation, or we can not resolve them automatically and instead keep all of the data so they can then resolve them manually. And basically, we have identified the majority vote as a good way to do this for non-numeric data, so strings and other things that cannot be compared mathematically. In which case there is basically a majority vote between values in order to select the value that most nodes have submitted. And other than that, we can also do outlier detection and then aggregation, which, however, requires more nodes to be reliable, because we need to be able to tell where the outliers are with a bit more accuracy. So to evaluate this, we built a test bed that actually two separate test beds technically, because one is doing the automated data acquisition and the other one is doing the cross-validation algorithm. And then basically we used our own real reference data, for example, the Docker Hub dataset I mentioned earlier, and also some others from the Artifact Observatory. And then we also created some fake data just to be able to better judge the performance scaling properties of the system we built. So when it comes to looking at the change in data quality, when we use majority voting for non-numeric data, basically we can replace any missing values that might be lost because any of those failures that we talked about before. Basically any values that are wrong or random or corrupted can be fixed as long as they're not present in the majority in this case. And when it comes to aggregation, if we have enough nodes, we can detect outliers and then make sure they are not affecting our ground truth value. Otherwise, we may have issues because random numbers will affect the end result. What we found in our sample data is that the nodes generally agree on most of the data. So because the dataset was pretty large, depending on the day, they agreed on 98 to 100% of that day's data snapshot. So basically, all of this conflict resolution was only really done to fix the remaining 2%. However, the biggest thing we found was that when there was an arbitrary amount of missing data on one node, we could use data from the other nodes to restore it, as long as it wasn't lost to the majority. Then we took a brief look at performance. Some of the experiments were also done over the network to measure the overhead, which, as you can see, because we were moving around datasets using Git, which is not very efficient, was most of the time of the execution in the network examples. And basically we observed that this scales linearly in most cases. You may have noticed in the last graph that there was a jump at 11 nodes, because that is when we start using the outlier detection, because below 10 samples it is actually not reliable. And basically, other than that, it scales linearly for the number of entries and also for the complexity of the entries. So how many fields each entry has, and also how many entries we have in the dataset. And we also found that the two different conflict resolution methods do not affect the performance in any significant way. So regardless of whether we're doing the majority vote or the aggregation, they're actually running at more or less the same speed. So there's no observable difference here. And moving on from this, basically, we now have the system. So we have the automatic reproducible acquisition, and we have this early cross-validation prototype. But essentially, we now want to evaluate this system in an end-to-end scenario. So basically say, okay, find a real use case and evaluate really how concretely improved the data is. And also basically investigating the implications of using this type of collaboration. So what is happening with provenance, what is happening with the data ownership, and also how feasible is it really to depend on this kind of automated verification versus actually doing some parts by hand? And with that, I come to the end of my presentation, so if you have any questions.
Thank you. We have time for questions. The phone is open.
Okay, you first and then.
Yeah, thanks for the presentation. I was wondering what kind of use cases did you have in mind, or which use cases did you use for the data? And I'm wondering whether the mechanisms to detect errors and to correct the errors, whether they might be very application dependent too.
Which is why we have this selectable behavior. And the idea is that the two methods we have now basically to resolve conflicts are not exhaustive. So if an application requires something different to be done, for example, to us to replace the aggregation methodology with clustering, for example, that might be integrated. So the idea is first we detect the conflicts just by saying that these nodes disagree on what the value of this should be. And then we figure out the conflict resolution. But this is basically a manual selection on behalf of whoever is designing the data set. They say, okay, for this field in the data, I want to use this conflict resolution. And so, okay, we have two methods now that we were evaluating with, but we can add more in the future.
But for example, if we would deploy here at the hotel some let's say 5 sensors, temperature sensors, so I would expect that the temperatures all differ in certain ways, or how would you handle that?
Yes, because in this case we would not expect an agreement. And that is a situation where this type of cross-validation would probably not want an automatic cross-validation. Because we do this when we expect the nodes to arrive at the same result. So when we expect the result to be reproducible. Reproducible in this case does not mean that we have 5 sensors in 5 different locations so we have the same temperature. It means we have some kind of experiment that at least to a large degree has a deterministic result, and we want to verify that that it actually is reproducible.
So I have Pierre and then Marcelo. Pierre?
Yes, if I well understood your evaluation of your performance, you didn't take into account the transmission of the data. Is it true or not? You mentioned in a slide, I don't see this.
Yes, so the transmission of the data is actually present as a factor in the two network examples. Basically, just because I wanted to show that for the most part with this implementation, the network overhead is most of the execution time in this case. But that is implementation dependent.
But in a decentralized system, one of the big problems is data transmission, especially the failure of the network. Because your scenario is not a machine here, a machine just aside, it's another part of the world. Then you have a lot of chance of network failure or delay. And how do you manage this kind of situation? Do you plan to do something to manage? Because you can receive the data the day after for some sites.
In these cases, we would use fixed checkpoints, and basically, yes, there is always a chance that a node would miss it, but that is basically what we are planning for in any case. So we are planning to have this redundancy exactly for that. So some nodes might fail to meet their deadline, and we will gauge whether or not we have enough data. And we also anyway produce some statistics at the end to show exactly how close we are to what we wanted to achieve. So then a user can look at all of those, can look at the logs of the system and say that, okay, well, there's too much deviation here. So even though the system thinks it has arrived at a good result, it's not good enough for me, for example.
Yeah. You mentioned that you
for testing you use some sort of fake data. Can you elaborate a bit more on that? Because if you do this, I mean, I don't believe you did it like I'm saying, but if you do this without paying attention, you can add some bias in your test. So how did you manage to?
So essentially, we used the real data as I used the real data as reference to create them. So I had 3 real data sets that we have from the MAU project, and then I basically tried to sort of create a spectrum of different data sets in terms of how big they are, what is their composition with regards to strings versus numbers, and also how many copies we are trying to cross-validate. So in this case, unless we are careless about introducing fake errors, this is usually the problem. In our case, we did this sort of, I did this sort of conflict resolution experiment using the real data. So I had some copies of the data and they disagreed on 2% of the values, and that's where we did the conflict resolution. Something I definitely want to look into in the future is to try and replicate this in the fake data as well. So try to inject random errors.
How do you do that? That's mostly my question.
That is something that is going to be hugely application specific for the data, because some data is more deterministic by design. So if we're looking at a public data source, it varies a lot. And if we're looking at an example with a fixed input data set and a fixed output data set, we don't expect any variance at all. So what I was planning to do is eventually test with different distributions of conflicts. If we have a lot of conflicts, what is the problem? If we have a lot of outliers, for example, how do we fix that? How does the system operate in these cases? So this is something I intend to investigate further anyway.
Any more questions? I have a few questions, but I would like to. Can I continue?
Yeah, go ahead.
So, when you're trying to assess the quality of your data collection system or your data-driven system, of course, you can figure out outliers, and you can figure out that, I mean, you can average values, you can do things like that. How about trying to, I mean, I'm thinking about many things that could be detected differently. I mean, it's just an error or a strange behavior in something in the data, I understand. But what about things that are correlated, or some things, for example, you could, for example, detect that some node is malfunctioning, because all data coming from there is bad. And then you actually can, in order to improve your computation based on this data, you can just, for a while, forget about this one.
Yes.
Did you think about something like that?
This is one of the possibilities for the further work. So basically, assessing the performance of nodes and assigning weights to their data is one possible solution for that. So kind of building a soft reputation system among the nodes. This is also possible. And another consideration is that this is only when it comes to divergent measurements for the same period of time. There is also the possibility for localized errors introduced by individual systems.
Yeah.
So a node was functioning well yesterday, but today is doing something strange.
Or
even
a thermometer that just never works in the afternoon, for example.
Yes. And that is also something very realistic. One of the problems we had with the node in Argentina is that eventually they cut its internet completely and it just stopped sending data. So this is something that happens especially when there is no single entity governing the whole system.
Exactly.
So these are all things that we want to test with a larger real-world deployment, not just test in 5 VMs in Zurich, and we want to extend this to exactly figure out what are all of these problems that only emerge when you have a large enough system.
So this brings to me a last question, if I have the right thing.
Yeah.
So your graphs there, it's good that you stopped there. So you have 22 nodes there in your test. Is there a reason for having, I mean, in my humble and not very knowledgeable opinion. So few nodes, but why don't you go to 20,000 or 20 million?
That is also possible. Of course, in this case, the network overhead would go off the chart, but in practice, exactly because this is separate entities and distributed among different institutions, I just think that there will never be a very big sort of cluster that will have thousands of nodes, simply because we would need to have 1,000 independent people operating them. So if our system cannot produce a useful improvement with a few nodes, then we have to rethink of the strategy for improving the data. Which is why I was evaluating with about 20 nodes, because that was a ballpark for the number of collaborators I hope to reach in the real world, basically.
But again, what kind of data did you consider that, for example, this Argentinian node, what kind of data did it produce?
So the Argentinian node actually operated for a very short amount of time, so it mostly ran some test data and also contributed a bit to the Docker Hub dataset, just a few days of operation, basically.
But what information was in there?
It was basically collecting metadata from the Docker Hub Marketplace API.
And what kind of ground truth do you have in such settings?
That depends on the data source. So in the case of public sources, they move around too fast.
Okay.
So in that case, you basically just want to prevent data loss from failures. So if some nodes fail, you want to be able to fill the gaps, essentially.
Okay.
Because the problem is, even if you synchronize all of the nodes running at the exact same time, one of them will run a bit slower and maybe a repository gets updated and then there is no agreement.
So we have to stop now. So thanks again. And let's move to the second speaker. And by the way, we are 28 in the room. I counted.
Yeah, I also made sure. I said 28,
yeah.
But I talked with the person who will actually make the sandwiches, and we have a choice. So maybe with the raise of hand.
Makes it difficult.
Cheese or ham?
We have a choice. Okay, so there is salami, ham, and cheese. So who is for cheese only? Please raise hand. 1, 2, and 3. Okay, so for the remaining 25, we have who is for salami? 1, 2, 3, 4. 4? So I guess the remaining 21 is for ham. Yes? So no need for raise of hand, no?
Just don't forget yourself, because last time you forgot yourself.
So my inference of was correct. So the fewest cheese, then salami, and then most 21 ham. Okay, then yeah, good. Thank you. Yeah.
Can we choose the bread?
Huh? What?
Can we choose the bread? The breakfast from this morning was excellent.
So I will tell you, use the same bread for the morning.
The bread with little black points inside.
I try. I do my best.
Very good.
Okay, thanks. That's it.
Thank you. Let's thank our organizer as well. So thank you. So the second speaker of this session is Alisson Medeiros from Uni Bern, and he will talk about mobile virtual reality services.
Hello everyone. First of all, thank you for the introduction. And today I'll talk about some recent work that we've been researching, and it's related to virtual reality. Today I will talk about some introductory concepts of the VR background. Then I'll give you some motivation points to support the realization of our research. Then I'll look at some related works and some limitations of this scenario, and then the research questions that we've been working in order to solve some problems in the current state of the art. and then I will present the proposal to try to answer the research questions. So basically, virtual reality is a technology that provides an artificial rendering of the real environment, and it provides this immersion level by providing audio and video resources and possible supplemented by other sensory devices. And virtual reality is capable to provide this level of immersion by providing realistic visuals, audio, and interactions. And to provide these kind of features, virtual reality users must use a specific equipment which is named head-mounted displays. So these these equipments are responsible to provide the virtualized world in the VR background. So it's very important, this kind of technology today, because it's expected to play a critical role in the city's future, and it will be very used for gaming, entertainment, education, and so on. Basically, to achieve the visions of future VR technology and applications, there are three specific areas that must be improved at the same time, and it's the visual, the sound, and the intuitive interactions. However, there are some specific requirements that must be met in order to achieve this kind of immersion level provided by future VR application. And we are interested in the investigation of the latency minimization, more specifically the computing latency minimization. And it's very important because this kind of lag for VR application can cause some health problems like sickness or even an uncomfortable and nauseating user experience, for example. So that's why we are very interested in trying to solve this type of problem for future VR applications. So advanced VR applications are composed of 6 DOF videos, or 6 degrees of videos. And this type of videos requires a low response delay, and this type of delay is composed by different tasks like the sensor delay, cloud edge processing delay, the network delay, request overhead, buffering, rendering, feedback, and so on. As you can see, there are several tasks that are responsible just to rendering the video for the user, the end user. And for some specific applications, these latency requirements, more specifically the computing latency requirements, are even more stringent. For example, for cloud-based VR gaming, for immersive deep presence, or even the video conferencing. So now I'll look at some limitations of the state of the art, which is very strictly related to the limitations of the current hardware for virtual reality technology. So the first limitation of the VR background is that mobility remains an issue, because if you consider the VR industry is most composed of stationary devices, and these stationary devices has some implications in the user freedom, for example. So the expectations is to have some kind of mobile virtual reality device, and one of the first devices that were launched in this year, if I'm not mistaken, is from Facebook, the Oculus Quest 2. So one of the main restrictions for this type of technology is the computing, the hardware limitations in terms of computing, because for future applications the current hardware is not enough, and the envisioned hardware for the VR technology will not be enough to deal with the next generation of VR applications. So the third limitation is related to the energy consumption, because if you just think, oh, we can just add more computing capabilities to the VR equipment and it will solve the whole problem that we have right now. But that's not true, because as soon as we add more computing resources, for example, we are changing the size of the device, the energy consumption demands, and so on. So that's not possible to just add more computing resources there and solve all our problems. So one of the solutions that we are considering to try to solve this type of limitations is to move the computing intensive tasks from the VR equipment to the edge of the network. And according to this strategy that we are considering, we've been working the elaboration of some research questions that we aim to answer through our solution. So the first research question is, what are the benefits of the multi-access edge computing to support the VR intensive computing tasks? The second one is, how would the VR refactoring or the offloading or extraction, could overcome the computational power required by VR AMDs? And the third one is, how to manage several VR services where each one is featuring distinct policies and requirements, and also considering the mobility aspects of the VR users. So to try to answer these questions, we propose the service chain graph. Service chain graph is a solution which aims to move the computation burden from the VR AMD to the edge of the network and supports the user mobility in this type of scenario. So basically, we just want to reduce the computation burden from VR AMDs in order to support future VR applications. And also, one of the main characteristics of our approach is to enable the management of these VR services that were extracted or offloaded to the edge of the network during the user mobility. So as we consider that these services could be deployed in the edge infrastructure, we have to deal with several of challenges that could arise with just this offloading option from the VR AMD to the edge of the network. So basically, one interesting point that we should consider is what kind of services could be offloaded or even extracted from the VR AMD to the edge of the network. So this is very important because the current state of the art just considers that offloading is a good solution for VR or AR, etc. But what kind of services should be considered in this process? Is there any negative impact during this offloading process? So these are some kind of type of questions that we are trying to answer here. And for example, we are considering some supplementary services that could help the VR applications to improve the user experience. And then we want to have an analysis of these specific services and then decide to where we have to deploy them and keep this mapping during the user mobility. So for example, the motion prediction service could be extracted from the VR AMD to the edge of the network, or even the mobility prediction services, field of view extraction, for example, or even the state transfer if we consider the service migration. However, there are some specific services which demands a lot of energy consumption. For example, the transcoding service. So this is very important because so far as we can see, there is no strategy that considers the transcoding offloading from the VR AMD to the edge of the network, for example, because this is a very complex task. However, we could have some enhancements in the VR equipment in order to achieve some specific features like reducing the equipment temperature, or even increasing the battery life in order to make that user more comfortable to use the application more time, let's say. So this is the overview of our solution, and basically we just decided that extract these services from the VR AMD to the edge of the network could be managed by applying different chains between these sources according to the dependencies. So we apply this type of strategy in order to try to reduce the possibility of latency bottlenecks in one of these chains. Because if you have only one chain, for example, and you have let's say some failure in one of them, the whole stack that depends from this source on will be affected. So you have some type of latency, and it will be noticed by the VR user, for example. And as I said before, there are some troubles that these users could face in terms of even health issues. So the key features of our solutions is to identify to where we should offload these sources, or even what kind of sources should be exactly offloaded, and why, when, to where. So this is very important to us. So basically, we went to find the appropriate edge server to offload the VR service before we starting this offloading process. And then we need to maintain the acceptable computational latency during the user mobility. Also, we also provide some type of trade-off analysis between if we really need to offload the service back to the VR AMD, or even considering the service migration. So it will be highly dependent on the mobility scenario itself, or even in the latency issues provided by the VR AMD equipment, or even the edge infrastructure available at that moment. So in order to deploy this concept, we provided an architecture, and this architecture is mainly composed by the SCG controller, the SCG agent, and the SCG NEC agent. Also, these architectural components are interconnected by an SDN controller, and the SCG agent, for example, SCG VR agent, more specifically, is deployed inside each VR equipment, and also have an edge infrastructure, a distributed edge infrastructure here, where we have one specific agent deployed in each server in order to have the knowledge of to where we should offload and what are the current resource availability that that specific node could offer for the mechanism, for example. So basically, the SCG controller is responsible to have the full view of the entire infrastructure, and it needs to know what are the available edge servers that could be used to offload some specific servers, and so on. Basically, just to summarize, the SCG MEC agent is responsible to check the resource availability in each MEC server. And then before that, we have prepared the environment in order to deploy some specific VR sources. So for this specific SCG MEC agent, we've been working before restarting our research in virtual reality in one edge mechanism that is responsible to provide the allocation of resources in edge infrastructure. And now we are considering this mechanism in our virtual reality scenario. So this paper was named React, and it was published at the Physical Communication Journal in this year, and it's named React, a solidarity-based LS subsea resource relocating strategy for multi-access edge computing. We are considering this mechanism because it can make sure that VR services that use a shared MEC and EC infrastructure, for example, could never run out of resources. So it's very important when you're talking about latency issues in this scenario. So it's responsible to deal with the scarcity of resources in edge infrastructure, and it adopts an adaptive solidarity approach to make sure that these sources could never run out of resources. So here are some results from our paper, and this first part of the results are related to the capability of the mechanism to provide resource allocations actions during the scarcity of resources. So we prove here that even though there is no more available resources in a specific edge server, we are still able to reallocate resources from less priority services to more priority services in order to keep every service running in a specific matter. So the second part of the results is related to how the mechanism could manage the service outages during the scarcity of the results. So sorry about that, but I forgot to mention that we are comparing our algorithm with the Kubernetes algorithm, and we mainly are considering a specific situation where there is no more available resources in the edge servers. So basically the first graph shows that we could avoid more services to be migrated or even have a negative effect due to the scarcity of resources. So the second graph is related to the resource reconfiguration attempts during these specific situations. The last part of the results is related to the amount of resources that could be saved during this scenario, and the last part is related to the algorithm time response, which is very close to the Kubernetes, as you can see here. So, just to conclude, the next steps of our research is to work in the evaluation scenario, and we are considering the new Facebook Oculus Quest 2 that we bought 1 month ago, and we are still working on how to manage these offloading strategies for this type of applications, because it's very important to point out here that the state of the art is very restricted in terms of how a real technology could be enhanced in terms of latency, network latency, or computer latency during these mobility actions, during a mobility scenario considering the offloading actions. So basically this is my presentation, and if you have any questions, please let me know.
Thank you. So we have time for a few questions. Yes.
So you're working in this field of VR that is, for the time being, very specific, where the usage are very specific, like gaming, medical rehabilitation, etc. And your work is to remove all those extreme requirements to try to solve them.
Basically, it's not to remove these extreme requirements, but to deal with them.
Yeah, absolutely. So in the future, your VR would be accessible to everyone, and we could use that everywhere very easily.
That's the idea, exactly.
What would then be the use cases?
So that's a good question. And for example, the mobility issues for VR is still very restricted. If you consider AR, it's more easy to provide a use case.
Absolutely.
However, if you consider right now mixed reality, where you can use sometimes VR and AR, then it makes more sense to have some kind of applications for cyclists or pedestrians or so on. But right now we don't have a specific application that I can tell you that we are working on. But this is some kind of work that we are thinking in the next generation of VR applications. For example, if you consider right now, we just have in the VR industry VR AMDs that are just stationary.
What's
So
AMDs? Sorry.
this is the VR equipment,
Right.
headset that you use to provide the virtualized work.
Yeah.
Get it?
Yeah, I do.
All right.
No questions?
Maybe I missed something, but could you very simply explain what you mean by intuitive interactions?
Yes. For example, of course, that now it's very hard to talk about these intuitive interactions because we don't have the direct technology available in the market, right? But let's say that in the future we could just have a glove that's responsible to provide you some vibrations in the environment. You could have the perception that you are just touching something. So it could be more realistic that the current VR technology provides to you right now, right? So basically that's what I mean with intuitive interactions. Because this is just one of the main characteristics of the VR, for example. Right now, VR technology, most of them, they are not, they don't have a specific sound system, let's say like a powerful headset, right? So the audio is not so accurate like it should be. And the interactions that we have right now, they are very limited. So this is something that will be improved for the next generation of VR technology.
Let's start here.
So you touched upon evaluating with VR mobility, the VR mobility scenario.
Yes.
So what exactly range of mobility do you consider evaluating with?
Right, nice question. So we are considering the 5G or even the 6G scenario, right? So with this type of scenario, we have much more cellular antennas, let's say, where the user will be, sorry about that, where the users will need to provide more handovers between cellular antennas, right? So the density of the network will be higher than we actually have right now. Okay, so this mobility scenario will be more related to 5G or 6G, you know.
Because my thought is that, from my understanding at least, the current generation of VR HMDs cannot even be operated outdoors.
Exactly. That's why they are, most of them are stationary, and if you consider a mobile device, for example, you can just use it for a few minutes, like 1 hour, and it's highly dependent on the application that you are running there, because the current VR application that we have right now, they are very simplistic, let's say, you know. So the advantages of future VR applications, they were not investigated so far because the hardware limitation is a huge problem right now.
So what is your experience with programming with the VRs like Oculus?
So basically, we don't want to program a VR application, but at the same time, we will need to do that because we need to extract some features from there and see what are the results in terms of latency that we could achieve with that, you know.
So my question was more, I understand that you don't want to do fancy applications, but you need to still operate at the level of the system of the VR headset. So how much access do you have to these layers that you might need to sort of modify, tune, or extend?
That's an interesting question, but right now, unfortunately, it's very early to answer this question because we just started exploring it 1 month ago. Because we just bought the equipment right now, so unfortunately, I'm not able to answer this right now.
What time?
Yes, last quick one. But, I mean, you asked 20 questions last time. And then maybe the next person will really get prepared.
Andre, you can answer. It's not a quick question, so.
Go on.
He's a friend now.
Can you show again the one of the last slides that showed the architecture? This one exactly.
This one, right.
You put these services on near the base station.
Exactly.
As far as I know, in Switzerland, it doesn't. The distance are not so large, so it doesn't really matter. So actually, all the MAC will be in one or what's for redundancy reasons several data centers. Now, how will that affect the fact that basically the MAC they are all combined in one physical location?
Yeah.
So the latency may not be such an issue, right?
The network latency maybe will not be an issue. That's why we are dealing with the computational latency. So as far as I know, some works are already considering the network latency is not an issue for future and current VR applications or AR or any kind of immersive technology that you can imagine. So the network latency will be able to offer the network latency capabilities for this type of applications. However, we are just interested in the computational latency, which is very restricted to the hardware limitations. But as I said, right now this scenario it's not true, right? Because we don't have the density of MAC services that the 5G scenario aims to have, for example, right? So whenever we have this massive MAC infrastructure, for example, there will be more need to handovers and system migrations and so on. So we can just use this edge infrastructure provided by the environment. Let's say a city that provides the 5G features, for example, with the whole density that's required by the scenario and so on. So it's much more easy to understand that this scenario could be applied in that specific situation. I'm not sure if I was.
No, that's what I'm saying. It's not a good question. Thank you.
Marcelo, why you say that? You can ask what question.
So now I have a few questions that I will not ask. It's about confusion that I had understanding your system. From the slides, I got confused by the control flow and data flow in your slides, so I'm not sure. Maybe there is something that you could improve. But I'm skipping that, we'll come later. But I have one question then. So you have a software-defined network, right? An SDN in the middle.
Yes.
And you're allocating services in you have to show it. So you have an SDN.
Yeah.
And then you are allocating services in these edge devices around, right? And they're connected by this SDN.
Yeah.
Shouldn't you handle them together?
What do you mean?
Like when you allocate a network, you must be sure that you have enough bandwidth to reach the node when you decide to put it somewhere.
What about the computing resources? Because, for example, as I mentioned before, we have several MAC servers, right? Then the user start moving from his initial location to another location. Then we have to deal with some kind of social migration or even the floating between the MAC servers and the user equipment, the VR user equipment, for example. So it's much more complicated than that, because you have to make sure that for everywhere that the user is moving from to, you have to make sure that you have as well networking bandwidth resources to be allocated for that specific actions as well as MAC resources in terms of
That's what I
RAM
said,
and
yeah.
CPU.
That's what I said.
Yes.
So I did, well, I will take this offline. I didn't understand.
Sorry if I didn't answer your question.
Okay, so thanks again. So we move to the last presentation. I don't know if I pronounced correctly. He'll talk about fog hosted services.
Hi everyone. Hi everyone. My name is Tofunmi Ajayi. I'm a second year PhD student at the University of Bern. Today I will be giving you a presentation on the current research work, which is towards an adaptive slicing framework for fog-hosted services. So the background for the content for today's talk is first we'll give you some general background information on the related to the topic that we're handling, and then we talk about resource allocation, which is essentially what is network slicing is based on, and then based on this we talk about our motivations, and then we introduce our proposed approach, which is still currently a work in progress. And then we just talk about the next steps of our work and then finally conclude. So we can start with the background. As we move from 4th generation networks to 5th generation networks and beyond, we're moving from networks where a lot of the network functions were based on were deployed on specialized hardware. So, for example, you had mobility management entities or serving gateways that were based on hardware that were specifically built to handle the functions, those functions. However, as we move to next generation networks, such as 5G, the idea is to go from more hardware-based networks to more software-based networks, where these network functions can be abstracted and deployed in cloud data centers, and cloud data centers far away, as was just said, and we can essentially move from hardware-based networks to software-based networks through network function virtualization. So what this means is we can abstract these network functions from the hardware they're based on, and then through software-defined networking, which provides better central control of the network. However, as was previously mentioned, some services that will be needed to support it require strict latency requirements. And this is where edge computing comes in, where we try to essentially offer the same capabilities of the cloud closer to the edge. So we try to offer communication computing capabilities closer to where the data generates, so that we can reduce the latency between where the data is generated and where it's computed. And this is ideal for time-sensitive services and applications. And also the idea of edge or fog computing is that it reduces the traffic congestion in the backhaul, since you don't have to send all the data generated at the edge through over long distances to the cloud. So one important aspect to understand is that moving from hardware-based networks to software-based networks requires that we would need to essentially support different services over the same infrastructure. And to do this, we need to find a way to allocate these resources amongst different services. And this is the next section. Sorry. And how to do this is through network slicing. So we want to essentially provide a way to create virtual networks over the infrastructure from one end, so from the edge of the network where there's the radio access network, to the core network. And this allows us to automate services much quicker. We can also provide orchestration. We can provide services on demand in an elastic manner. We can extend services and how they're provided. We can also offer better protection. And this, essentially, we can deploy these network functions and over the infrastructure as different, as part of a slice, essentially. So you can imagine if you have an infrastructure and you have to support different services, you have to be able to find a way to allocate resources to each of these services. and this is the next section of our talk. So, existing or state-of-the-art approaches are based on optimization, goals, where other people have looked at exact algorithms, heuristics, approaches, or bio-inspired approaches like particle swarm optimization or genetic algorithms. However, we see the disadvantage is that these approaches might require frequent configurations. More recently, there has been a push towards using machine learning to allocate resources in such environments. So, for example, using neural networks to forecast the demand of the services in the future, and then based on this kind of prediction of forecasting, allocate resources ahead of time. However, one of the biggest problems with this is the need for labeled data. So if you want to use this kind of approaches, you need to essentially be able to label data, which can be quite costly and difficult. You also need to be able to, another advantage is the fact that it's possible to have incorrect predictions. And to cap off the point is, it's important to understand that services are constantly evolving. As users join the network and leave the network load essentially shrinks, and it resources become available and utilized as network as users leave and join the network, and so the current service pattern is essentially changing in a dynamic fashion. And even more recently, outside of machine learning, reinforcement learning has been used for dynamically allocating resources. So the general reinforcement learning framework is you have a state, and then you take an action, and the action essentially determines the next state of the environment, and based on the state that you based on the state of the network or the environment, you get a reward. And this is great. However, the typical reinforcement learning frameworks assume that the next state depends on the selected action. However, in wireless networks, which are dynamic and essentially unpredictable, this might not be the best approach. And this is essentially what leads to our motivation. So, sorry. Just a general recap, network softwareization brings many benefits. So we can essentially provide programmability and flexibility, but also brings several challenges. So we have to essentially find a way to share the limited resources of the infrastructure across different services. And a lot of the infrastructure, for example, in the edge, are limited by the capacity. So conventional resource allocation approaches, such as the ones we mentioned, like optimization-based approaches or neural network-based approaches, are unsuitable for adapting sliced resources. So we need new approaches that can adapt or reconfigure slice resources that can suit varying network states and different contexts. So the question is, how do we allocate or schedule resources in the face of unpredictability? So here we give a simple example scenario. So if we imagine that at a certain time we have this fog device that hosts 3 services, and then based on this scenario or this situation, it allocates this amount of resources to each fog service. However, because the network is constantly changing and users are constantly joining and leaving the network, at a future time step, the question is, how do we essentially allocate more resources to meet this increase in demand? So a proposed approach, which is again a work in progress, is based on online and model-free learning. So the goal is to develop a framework that can adapt sliced resources in a dynamic and online manner to handle unpredictable network loads. And also it's based on a model-free approach, so we want to make little or no assumptions about the network state or the environment. And then we're also motivated by the fact that learning or this online learning approach is being increasingly used or applied to network slicing. So for example, state-of-the-art works are using reinforcement learning, such as Q-learning, to deal with dynamic slice requests, and others are using deep reinforcement learning again to deal with uncertain slice requests. So our proposal is based on a multi-armed bandit framework, which is a form of associative reinforcement learning. Over here you see what makes the difference between, for example, multi-armed bandits, decision theory, reinforcement learning, and Markov decision processes. So with reinforcement learning, like I said, the actions that for example, agent takes change the state of the world at the next time. However, like I said, we want to essentially have a model free. We want to make basically no assumptions about the state of the world at the next time. So, and this is essentially what multi-armed bandits provide us with. So, multi-armed bandits have been used in healthcare. They'll also be used as part of recommendation systems, and more recently, we're seeing them used in telecommunications environments. It's essentially a simplified approach, which does this similar thing, which does something similar to reinforcement learning, but it avoids the complexities of reinforcement learning. So, for example, the chosen arm that we take doesn't have a delayed effect as you would, or the chosen action we take doesn't have a delayed effect, as might be the case in typical reinforcement learning. More specifically, our approach is based on contextual bandits. Going back to the point is we have a infrastructure, or for example, we have an infrastructure that we have to allocate resources that hosts different services, and we have to allocate resources to these services in order to meet the quality of service requirements or some KPIs. And the contextual bandit approach essentially provides us with a way to do this by considering the context of the network. So for each round, for every decision round, the algorithm essentially observes the context, where the context can be infrastructure, the amount of resources that a service is using. It could be the culture of service, the current culture of service requirements of a service. And so based on this context that the algorithm sees, the algorithm picks an action. For example, it can decide to allocate a certain slice, a certain amount of CPU and a certain amount of memory. And then based on this action, it receives a reward. So it sees an n-dimensional context vector, and then the rewards, unlike reinforcement learning, full reinforcement learning, the rewards are essentially context and action-based. And this essentially minimizes the dependency on having this state transition models that you see in typical reinforcement learning frameworks. Just to enhance the edge scenario we saw earlier, we have an agent, this contextual multi-armed bandit agent, that essentially monitors services and the network resources, so you can monitor compute resources, radio resources, and storage resources, and receives the state of the network at essentially every discrete time step. And then based on this information and based on some overall reward, it can essentially compute a new resource allocation based on the previous reward, it got from the previous action it took, and the current context of the network. So essentially, what we're trying to do is we want to make decisions that, we want the agent to make decisions that are best for the resources, the current resources, based on the current state of the network. So the next steps is to finish the implementation of the framework that we're working on. To evaluate the framework, there's currently a data set about the resource consumptions of different network services, so we'll be looking to use that. But we're also looking to essentially also generate our own data from different application services. Or even further down, we can consider, right now we're only considering a single fog node or edge node. And perhaps down the line, we consider maybe multiple devices that form part of the edge layer, and then how to essentially control the resource allocations of each device in a decentralized manner. So, in conclusion, we have seen that moving from fourth generation networks where the network was based on specialized hardware to fifth generation or sixth generation networks, it's important. NFV and SDN have provide us with technologies to be able to softwareize the network. Fog computing or edge computing and network slicing essentially facilitate a way to support a new range of 5G applications by bringing cloud computing resources closer to the edge, and essentially allocating the resources of this edge infrastructure to meet the quality of service or requirements of these quality of service requirements of these different services. And we've seen that conventional resource allocation approaches are not necessarily suitable when you bring the impact of uncertainty, which is common in wireless networks, into the problem. And then we also see that it's important to have new resource allocation approaches to mitigate this unpredictability at the edge. And we have motivated the use of online model-free learning to adapt fog resources to meet site-specific services. And this is the end of the presentation.
Thank you. Now we have 10 minutes for questions.
Yes, I have a couple of questions on this uncertainty. What I don't get is, what is uncertain? Is that you get data over the network, over the situation that this data is incomplete, or is it the environment that changes?
Yes.
So the data is obsolete, essentially.
Yes, you can say that at every time step, the data that you had from before could be obsolete.
Right. Okay. So then the regular approaches, they give you a solution that is not really robust.
Yes.
Okay.
Yeah.
And then the last question is, for me, how can you predict uncertainty? Because you said that we're using machine learning, so we're trying to learn about something that is unpredictable. So
no, we're not trying to predict. We're trying to adapt. That's the difference. If you're trying to predict, you're assuming that you can model the stochastic. But if you're trying to adapt, you're saying, okay, based on what I know, what I see, then I'm going to adapt to. So it's a bit of trial and error initially, but over time, as you learn more, you improve how you allocate these resources.
So are you trying to basically learn how to make something more robust to uncertainty?
Yes, exactly.
All right.
The nature of the data that you have,
yes,
is it can be characterized as a high level of randomness, let's say.
Yes, you could say that.
Yeah, because the underlying processes are human choosing to use the network or not.
Yes.
And in this case, do you know a bit the difference of the performance of the machine learning methods and the Q-learning ones?
Oh, no, I can't say I do. Sorry, but it could be something I can look into.
Yeah.
If you allow me a comment, this is a comment, it's not a question.
Yeah,
Once the network operator was telling me that he was never applying the solution of the algorithm because he couldn't understand it.
Okay.
So he was applying his own thing, which was actually more robust.
Okay.
In his mind.
Mm-hmm. Can you put your slide where you show this comparison with the multi-arm bandit, reinforcement learning, so forth? And you said the action don't change state of the world.
Yes.
So you change only the reward, or if you don't change the world, then why do you have any action?
No, the idea is that you change how much resources you allocate to the different slices or the different services, but because the services are dependent on the outside world, so how the outside world changes, then you're essentially adapting to how the outside world changes over time. So you don't change the world because you can't change how users enter and join the network or leave the network, but then how those users enter and join, leave and enter the network determines how much resources are required for the services. So you're trying to adapt to this external world, which determines how much resources that the service you're looking at provides. I don't know if that makes. So okay, you have a service that supports network users, right? And as network users come in and out of the network, the amount of resources that you need to allocate to the service changes, right? So what you want to do is that as network users leave and join the network, you adapt the resource allocation for the service to meet this dynamic nature of the network. I don't know if that's what
Okay.
You don't.
No, maybe it's in the previous description, like when you have the reinforcement learning, the classical picture where you have state,
right,
state action,
yeah,
and there you see the action change the
Yes.
state. You say you remove.
Yes.
You remove that.
Yes.
But then, in a way, if you don't impose the action, if they don't change anything to the state,
right,
then the reward will not change. You say that you change the. You say you have that dotted line here,
right,
where the reward, the action change only the reward.
Yes, essentially.
And that's what you mean, that you have some, the state doesn't change at all, and then it doesn't matter, then you give some action, and that's how do you change the reward if you don't go through observing something?
So the reward is essentially based on general reinforcement learning. The action does yes, the action also impacts the reward, but the difference between this approach and the context and the multi-advantage approach here is that the reward is based on the action and the state.
Yeah, but that's I guess
So
it's there. This
previously you had the action determining the next state. So here you have the action does not determine the next state. So you're trying to learn a policy that essentially maximizes the reward for a given state and for a given action. That's essentially it.
Mm-hmm.
Yeah.
But can you not consider the resource allocation also as a kind of state?
In what sense, maybe?
I mean, if you allocate resources to different slices, the resource allocation itself could also be considered as a state or not.
Yes, yeah. That's
So in that case, you would change the state, at least partly. If you increase or decrease the resources.
Yeah, that's.
It's not a state that should be done. It wouldn't on the outside world.
Yes, yeah, it's more. It's possible to consider, but that's not really what we're.
Okay, so we're perfectly on time for the break. It's 10:30. If you don't have any more questions, so thank you very much. So we'll have a coffee break and.
Okay, everybody, we are nearing or converging the point of being complete. We don't know when we will reach that point, but we will nevertheless start. So, welcome to the session on networking part 2. We will have 3 talks. The first talk is given by Isabelly Rocha on developing, I think, a better parameter tuning server for inference in DNNs. So please.
Thank you for the introduction. So I will start directly by talking a little bit about the concept of parameters tuning and machine learning applications. So taking this typical example of image classification. So once you have your data set pre-processed, you have the label data that you need, and also your architecture defined, so you can start this training process, right, where you're learning the model parameters. But before you do that, there are also some other parameters that you need to set before, which are called the hyperparameters. And they are things like the number of layers you're using in your architecture, dropout rate, or some more training-related tunings like number of epochs and batch size. And this is like a state-of-the-art problem, and then the first question that we start asking here is what else has to be tuned in there, right? So to think about this problem, we look here at an example of a workload of a ResNet with a Cipher 10. where we increase the number of GPUs that we are using for the training process. And what we see is that, like, with a small batch size, like in this case here 32, this does not really scale. It's the opposite, right? The runtime is increasing and the energy reflects on that. And if you have larger batch sizes, we see something similar, just that also it stops there, like between 4 and 8 GPUs, we don't really see much difference. So it's also like a matter of like how much resource you should put into that, and this also depends on the workload, number of nodes you're using, the platform you're using, several things. So this adds a little bit more of complexity to the problem of tuning, parameters tuning in general. And then the next question that we could ask is, how about inference, right? Once you have your model tuned, trained, the next step would be to perform inference, and are there also parameters there that we need to consider, that we need to tune? And to talk about inference, then first we need to think about how this process works, right? So you can think about different scenarios. For example, here the topper case is where each query contains n samples arriving at a fixed frequency. And then the inference engine has to take the decision of how will you split that batch of samples in the way that you take the most out of your models. That's one way of looking at it. The other way is when you have a single sample queries arriving randomly, following a certain distribution. And here, like if you perform single sampled inferences, then what might happen is that when you reach the full capacity of your inference engine, then you're increasing the queuing duration, which would then decrease the overall average time, and this is also not what we want. So a better strategy could be to then batch it and then perform multiple image inference. But also we need to be careful on the amount of this like batching, because we also don't want to aggregate too many data, since like we want to keep this inference as fast as possible. And then when it comes to system parameters, also in the inference side, then here I have something similar for the same workload as before, just looking now at the inference side of the problem and increasing the number of CPU cores that we use instead of the GPUs, since now it's like inference and not training. And then here what we see is like if you're doing in a single batch equals 1 means you're doing a single sample, so obviously you're not really increasing anything when you add on the throughput case, when you add more cores, and even you are then spending more energy because you're using more resources, and that's not really what we want. So we want to do it in a more frugal way, and then be also aware of this. In the case where we have more samples, like here in this specific example, batch equals 100, then we see that the throughput scales better. But also again, if you compare like 2 and 4, throughput, the throughput difference, the throughput gain from 2 to 4 is not really much, but you have some increase in the energy there. So one thing you also need to consider is what are the user's priorities, right? You need to see what's the objective of the user and take that also into account. So those are all parameters that also need to be considered during this full tuning process. And then, considering all of that, we have designed this inference-aware multi-parameter tuning framework, which we called EdgeTune. And here what happens is like the user basically needs to define the workload, so the model and the data set that it wants to use, the parameters that it wants to consider, and then a range of values that these parameters can assume. And then all the tuning of what we discussed before will then happen as a black box for the user, which is described here in this right part. And then as output, we will have the trained model, the set of optimal tuning parameters, so that if the user decides to retrain that model, it does not need to redo the tuning, right? It can just reuse what we already found here. And on top of that, which is another contribution of this work, is that we also do then the inference recommendation. So currently the tuning frameworks that are available, they just really focus on the training. And here we say, well, it would be nice if we use the time that we have for tuning to also verify what would be the best way to perform the inference on the model we are tuning, since many users, they finish and then they don't really know what to, like where to deploy the model for the inference. If you're not an expert, it's not a straightforward decision, so we then also automatize it in the process. And just to in general lines here, so the general idea is that for each parameter configuration, we use it to train the model with a fixed number of training iterations or part of the data. And then we evaluate the parameters configuration according to the trained model on that specific trial. And we use tuning algorithms to choose the best parameters configuration according to the evaluation results. So in general lines, that's what's going on in this right part. So just to go more into details there are different ways to implement that. So we could, for instance, first tune the hyperparameters isolated without considering any system parameters, and then take just the one resulting solution and then perform the system parameters on that one. But this would mean that we are making the assumption that they don't influence each other, which is not really the case, right? We saw some previous examples where we see that this differs, like the system parameters vary depending on the hyperparameters that you're using. So we want to do that in one go, and therefore we implement this one-fold solution where we consider hyper and system parameters tuning done all together. And then also, this also obviously follow a searching algorithm, right? So there are different ways of doing the searching of parameters. So for instance, a really basic one is doing a grid search, right? Where you basically just try all the combinations in a systematic way. You can do then a random search, which handles the unimportance dimension a little bit better. But then there are algorithms such as Hyperband or BOHB, which then gives more focus to more promising configurations. So you do a more goal-oriented kind of tuning. And this is done based on successive halving algorithms and multi-fidelity budgets. So just to go a bit more in details of what that is. So the idea is that we initialize this whole process with n random configurations on the smallest budget possible. Then we evaluate all the configurations and keep the top 1 to ETA fraction. So for instance, if ETA is 2, then we are always reducing to the half of the configurations that we consider. And at the same time, we increase the budget per configuration via this reduction factor. Then we repeat this until the maximum per configuration is reached. So here in the plot there on your left side, you can see that more visually. So we start with 8 possible configurations. Then we drop to 4, the 4 most promising ones, which are the one with the lowest loss. And we also increase the budget from 12.5 to 25%. And we keep on doing that. So next one we have 2 and increase the budget to 50. And then you have the last one where you do the 100% also for verification. Then how you define this budget can also be done differently. So a typical way is doing based either on epochs or on data sets. So you take portions of the epochs, but you train on the full data set for each trial. Or you do the opposite, you take a fixed number of epochs and then you vary, you always increase the number of the fraction of the data set that you use in the trials. And then one thing that we propose here is to combine also these both strategies and then use a multi-budget approach which increments both of them simultaneously. Why we do that? Because we want to achieve this budget which has a small granularity, right? So it's moving fast once you have many configurations possible. But also we want that the accuracy of these trials is significant enough so that we can identify which are the most promising cases and then narrow down the search space. And here we can see that we're like in comparison with epochs and dataset, we are here in accuracy, you are in between these two. So epochs perform better with respect to accuracy, but if you look at the duration, it also takes much longer. So we then find this caught in between these two dimensions, which is what we were trying to achieve. And then for the last main part of this framework is this component where we do the inference parameters tuning. So at first, what we thought about doing there was having we had this assumption that the inference phase is the same as the forward phase of training, which is in theory it is the case. But when you go to the practice, we did some profiling of the both phases and also some extra experiments, and what we noticed that there are in practice some difference, especially considering the memory, mostly because of the weights, which during training are constantly being updated, and in the inference these are already like trained and fixed values, so there is this difference there. So we moved from this idea, and as an alternative, what we did was just having a simulation of edge devices on our tuning server. And to not add any overhead to do this inference tuning also, what we do is, since the inference tuning is just focused on performance and not accuracy, once the trial starts, you don't really need to wait until it ends to do the inference tuning, because we can just initialize it with random values, right? So we're not really interested in the accuracy, so you can randomly initialize the architecture. At the beginning of a trial, you know how the architecture looks like. So we can do that in asynchronously, and it's not really affecting the main tuning process. And then just to give a little bit of overview on the evaluation. So we took three main areas of workload. So here, image classification, one workload with speech recognition, and another one on natural language processing. And then we tested the prototype of our EdgeTune framework with comparing as baseline another tuning framework from Ray, which is called Tune. And one of the observations that we made was, here on this left side you see the absolute values for the Tune case, and then on the right side is the difference of our results with comparison to the baseline. And what we see here is that even though we are adding more features than what Tune is doing, we can still also, based on all these small optimizations that I mentioned before, also optimize the overall tuning duration and then also energy consumption in this case. So just to wrap it all up, the proposed approach covers multi-parameter tuning in a one-fold solution, which succeeds to achieve multiple layers of optimization objectives combined. We introduce also a multi-budget approach for the training trials, which reduces their runtime, but maintains the level of accuracy necessary for efficient convergency. And we demonstrate performance gains on runtime and energy measurements using state-of-the-art workloads. So this is it. Thank you.
So thank you for the talk. We are very well in time, so we have time for quite a few questions.
I'm well aware of hyperparameter tuning, right? And it's new to me, the system parameter tuning. Could you give some example of the most prominent, important, let's say, parameters, system parameters that we need to tune?
So for training, I was mainly looking at the number of CPUs. This is distributed training also, so this is having an impact. And then if you're doing on a CPU, it's mainly like the processing related things, because this also has an impact on the hyperparameters. So depending, like indirectly, this affects the accuracy, because depending on the hyperparameters that you're using, you might need different configurations into there. So if you tune the hyperparameters, you might be able to then indirectly optimize your accuracy as well. But which system parameters which I looked into was more GPUs, like the number of nodes that I'm using for the computing, and memory.
More questions?
I have a similar question to the previous question. You talking about inference tuning. So this process, can you briefly elaborate? Is it the same as tuning the parameters for the model, or how does it work?
Sorry, can you repeat your question? I'm not sure I got it.
I want to understand more on inference tuning.
Yeah?
What are you tuning? Also the parameters of the model, or you're tuning?
No, that's from kind of parameters where you can see is like the batch size, so the number of samples you're performing the inference on at the same time, and then the system parameters. The model is defined, right, because you're in the inference phase. So in that phase, the model is defined. It's just on the performance side.
I wonder in your last slide where you compare the various models, and maybe you can show it again. I was wondering if there's before that or after. Near the end where you summarize your performance result. Yeah, here.
Here.
Yes. There is some intuition into the multi-parameter that can speed up the environment, can speed up the process. You can say that now with your the one that has been chosen in the range, in the beginning you give the hyperparameter, and if I understand correctly, the system chooses the best range of hyperparameter to test, to try.
Right.
And can you gather some intuition for image classification? You should do, I don't know, this or that. It's better to do this, and speech recognition is better to do something different. In NLP, something different, or it's not explainable. Like in all machine learning, in a way, there is some of explainable AI, right? But so I was wondering if you could gather some kind of explainability in this search for speed.
Yeah, like actually, like the ranges, they are also defined by the user. So I don't define the ranges. You need to tell as input like what are the parameters and what's the range of values they can assume, and then it's. I don't know if maybe there is a generalization that you can do for different areas. I'm not aware of them. So that the searching algorithm is really looking specific to the workload you give, because it really varies. Even if it's the same workload, and then you're using different parameters, different ranges, then you can have different results. So as far as I know, it's not something that you can generalize.
Okay.
Yeah.
It's hard to get some guidance if you don't have that tool.
Right, that's why the tools exist, because
when an approach a new problem, I was wondering if there is a way to guide the intuition of.
Yeah, there is not, but that's also the reason why this kind of auto-tuners exist. There are many of them, right? There are like some in the cloud which are available. There are some open source ones, and the objective is exactly this, because with those tools you can even, like, if you're not sure what model you have, how your model should look like, then it can automatically tune it for you. It can create your network. Then at the end, like, to interpret what you get, then it's another story, but it's at least reaching the minimum accuracy that the user defines. But it's more a trial and error thing at the end of the day. Just in a smarter way, yeah.
So last question, Antonio?
Yes, okay, thank you for the presentation. Here, in the end of the day, you are performing a global optimization of a system, right? So you have a heat map there of that represents a space of parameters, and you have to find the global maximum, right? So global optimization is an immense field. There are so many global methods, and here, from what we see from the fixing the different budget levels, and you basically cut the worst performing individuals, so to let the best ones to keep going. It reminds a lot of genetic algorithms. So this evolutionary, where you just basically let the best individual go and you kill the worst performing ones. But in particular here, you select one specific global optimization algorithm. So the question is, have you tried to see how this tuning performs with other types of global optimization algorithms? For example, NSGA2 or other many of them.
So I did try some, like some of them, not many. Like I tried the more like straightforward ones, and then I tried the hyperband alone, which is another algorithm. And this, the BOHB, is like then something on top of hyperband, which I also tried. But this is like the framework, the prototype that I have at the moment. You can plug those algorithms, whatever you want. I didn't do a systematic testing on the type of algorithms, because from the state of the art, the successive halving algorithm, they already showed to perform well, so I kind of focused more on that. But yeah, it would be interesting to compare.
So there are studies who show already that the BOHB is already one of the best performing.
Yeah.
Okay.
Yeah. This is state of the art work. Yeah,
okay,
there is.
Then.
Yeah.
Okay, thanks again, Isabelly. Next we got Diego Oliveira, who wants to convince us that we need to bring SDNs into communicating cars and how to do this in the best manner. The slides are on that notebook, right? The slides are on that notebook?
Yes.
Yeah, okay.
Should be. So what was said, I'll try to convince you guys that we need to bring SDN into communicating cars. No, but basically the idea today is to give a bit of an overview of what is my PhD project, and then I'll talk about a recent study that we have done that's entitled towards SDN-enabled hashless make-before-break handover in CV2X scenarios. And my name is Diego, as I was presented before. So I'll start talking a bit about these future applications. So basically here I brought a table with some applications and use cases. Some of them are kind of well known, like as augmented reality was talking a lot, and also we have something related to autonomous driving, like pre-crash sensing warning, also automated overtaking, so how to do these maneuverings. And then from institutions like the 3GPP, the institution that specifies things like 3G, 4G, 5G, and so on, they analyze these use cases and they come up with some numbers that are the requirements that these applications need in order to run, and that's the latency column over here. There are other requirements in terms of other variables, but I'm mostly focusing on the latency, and that's why I brought it here. And then you might look here, we have something like on the 50 milliseconds range, 20, 10, even like not so popular application like electricity distribution, 5 milliseconds. And these might, some of these might look easy to achieve if you're talking about like wired communication, if you have a computer plugged to the wall and you can get these, some of these easily. But the thing is, we're talking about cellular communication, so it's hundreds of users connected to an antenna, and then it starts being more difficult to meet these requirements. One of the ways, one of the strategies to actually help to meet those requirements is to bring computing closer. So we have this edge compute binding messages and the router solicitation message RS and PDU. This is still a reactive handover, so it's a bit easier to describe, and I'll soon show a proactive one and also our approach. So our idea then was to try to fix these operations using SDN. So basically, we try to merge the lower level operations with the SDN operation. So we build this signaling protocol here. And also we try to account for the exchange of this CTI information that would allow us to not have to perform the hash. The biggest challenge here then is one, actually in the next slide I have the comparison, so it's better to show what's the difference. So this now is the proactive handover. It was also proposed by the same author of the previous one, the reactive handover. And the most difference here is one, the operations here, as you see, they have a detachment right at the beginning of the handover procedure, while we can just have the detachment much later. So this comes from the make before break, and then by these I have a series of advantages. So everything, it's kind of proactive because everything, all the communication flow is also prepared, and also I can recover of failures in case something goes wrong. I'm still not disconnected from the previous base station. And also we have this message here. So if we look both in this and in the reactive proposition, we have the PBU being sent from the target base station to the controller, back to the target base station, and then back to the unit. So I don't have any message that allow me to collect the clock references from the target and previous base station. And then, by creating another message and changing the order that they are sent, we actually send a message that passes by the target base station to the previous base station. Each one embeds its time clock references, and then it goes to the user, so it allows it to realize this rushless handover. It could be done without exchanging these messages if the network was synchronized, so you don't have to care about time alignments and things like that. These are the two main differences. And then we evaluated this. Well, we used two simulators, one for urban mobility and one for networking. And also on top of those, we used some frameworks for network simulation that work with those simulators there. In the evaluated scenario, we had this topology here. So basically, we have vehicles that are moving along this red line here on a highway. And we have some fixed nodes, the black ones, and also the blue and the red. The blue is where we place the SDN controller, and the red is one where the application was hosted. And then these white nodes here, we were changing them to kind of change the coverage of the scenario. So if we put them closer, we have a better coverage. If we put them much further, we have a bit of a worse coverage. One thing here is that all the scenario is at the edge. So the other proposition was they compared with a scenario where part of the network was subject to cloud, the links, the wide links was subject to delays involving the core of the network. Here are some results that we evaluated. Basically, we evaluated two variables, the handover execution time and the handover system cost. So the system cost is defined by this equation here. So a cost of a given handover H is the weight of the message, every message that's exchanged in that handover during the signaling protocol execution. Basically, it's the size of the packet times the weight of a link. So the links are, we have wired and wireless links, and the wired links were weighted as 1, and the wireless links was weighted as 10, as they have a much higher cost to be used in this case, which means that everything's at the edge. So as you see here, we have our distributions, this last one. I forgot to mention, but I briefly mentioned that when we do this procedure, the hashless, we have to be at a certain point where the user has connection to both the previous and the target base station. However, when it does not happen, or we do not have that positioning, we have to actually go back and fall back to the hash handover. So that's why we observe this distribution here, because we have the hashless handovers and hash handovers here, so we have these two modes. While the other propositions, they both use only the hash handover, so they focus most on the higher end over there. And these, to the system cost, we had some high values, although the average kind of lies in between the reactive and the proactive approaches. Here, we started then variating the coverage. As I said, better coverage gives more opportunities to have the hashless handover. Would it affect both the time and a bit also the system cost? And the results then, so as these always use the hash handover, they are kind of limited by there, so they are around this 60 milliseconds mark. And then ours, when we have a better coverage, so the base station was positioned closer to each other, so 100 meters average distance between them, we had better results that started increasing as the coverage as the topology gets more sparse. And here the cost, we have just one case, just one case where we had a higher cost than the proactive handover, but in general, we kind of lie in between them, the two proposals of the literature. So I have some final remarks with some takeaways and limitations. So we propose this handover that merges the lower layer operations of the SDN with the actual handover that's happening. We use these modern handover methodologies, the hashless and the make before break, and we show that we can decrease the handover execution time. With that, we also explored how the coverage has an impact on using those technologies that are not implemented yet, how the coverage of the scenario impacts that. And finally, we simulate all the environment at the edge, so there's no traffic subject to core network, which is what we're expecting to have for those low latency applications that I presented at the beginning. So we had some limitations also. So we did not evaluate the decision process of like how, if I have n available base station, which is the better one to connect, given we just evaluate the signal quality, but not like the mobility of the users, for instance, could be considered, so I could reduce the amount of handover operations and things like that. Also, we did not perform a very exploratory analysis in the sense that we would like to improve these by adding things like exploring handle mobility, different vehicular speed, and also changing more the topology. We did a very contained variation of the topology. Here's just to give a bit of an idea of the next step. So as I said, we're dealing with this service mobility and user mobility, and so we start moving a bit now in the next works towards managing the service mobility. And our idea is to work with using again the SDN to propose a way to address services based on their naming. So it's based on evolution of ICN and also SCN, so information-centric networking, so service-centric networking, where instead of addressing services by the address, the IP address of the host where it's running, we actually address the service by the name of the service. There are some propositions in the literature, and our idea is then to actually use some of the headers that would not be used. So for instance, I have the IP source and destination, as I'm not caring about where is the IP location of those services, like actually these would not be used, so we can actually hash the name of the service and put into these headers to do the addressing based on the name of the service. And these could coexist with the IP protocols, because we have this IP proto header that could be used to flag what protocol we are using, if we're using this SDSCN that I'm proposing.
Anchor-free, ranging likelihood-based cooperative localization. Now, this presentation is divided into 4 parts. At first, there is the introduction part, where we will see the background of cooperative localization. Then we will see and we'll explain how LCL works. Thirdly, we will see how we evaluated this proposed methodology, this new method. And finally, we will see the evaluation of the results of this evaluation. So, as the title suggests, everything here is about localization. Or in simple words, how to use signals to identify the position of an entity in space, like someone is using his smartphone and Google Maps. So, although in such systems more signals tend to typically lead to better performance, we haven't seen yet any effective cooperation among those anchors or agents or nodes to get indeed access to these to more signals and to more information. And this is basically the key motivation behind our work. Now, another term we need to clarify is the term ranging, because ALCL is based on ranging techniques. So ranging is simply the estimation of a distance based on some signal measurements, either one measurement or more. And lately, technology has lately indeed introduced important improvements for ranging, like the integration of ultra-wideband modules in smartphones, like the new Galaxy Ultra S21, which can offer, in theory, accuracy of even centimeters. Now, let's talk about some application of cooperative localization. To begin with, the most obvious one is the increasing accuracy. And the bigger the swarm of nodes is, the faster the information increases, so this is good. And this holds even in cases where we have limited to even no infrastructure, the so-called anchor-free localization, which ARLCL can perform. Or another application with even recent character is, for example, COVID tracking. Or a more exotic one could be cooperative SLAM, but now using drones in unknown environments, maybe in a search and rescue case. Okay, so at this point we need to mention that if the problem of anchor-free, ranging-based, not likelihood, and cooperative localization sounds quite specific, Imagine that today there is already a well-known and respected technique to do exactly this, to tackle exactly this problem. And the technique is called mass spring localization. To get an idea of how this works, you can imagine a set of nodes that have unknown to us positions and some noisy estimations of their in-between distances. And so, by considering the above as a system of masses and springs instead of agents or nodes and distances, like the figure on the left, mass spring optimization is using laws of physics to identify at which position these masses get as a system reach an equilibrium. The springs, if you release them, they reach an equilibrium. Yet the problem here is that this approach assigns the same importance to each distance, each spring, let's say. So either it's a small spring, it has the same importance as a long spring. And that is often not the case. So the idea behind the introduction of the term likelihood here at our project is to find a way to consider during the cooperative localization process the different uncertainties which are involved during the ranging process, and this way be able to assign accordingly proper weights to each one of them. It is also quite important to mention that our proposed method is actually technology agnostic. Okay, in our case we will be using BLE signals, low energy Bluetooth signals, because we have Raspberry Pis, but any technology that can offer ranging, we can use it. So to do that, we need a probabilistic model that can answer the following question. For example, given that node A received from node B this measurement, let's say a signal strength, how likely is that node B is X meters far? So we need a function to answer in every time this question. So to produce this model, this function, we deployed inside the room, a lecture room, a swarm of 21 Raspberry Pis. And we used a laser scanner, LiDAR, to record their true positions, to have a ground truth. Then we let them communicate with each other for 5 minutes, during which each Raspberry was recording the signal strength coming from all their others. The received signal strength, the RSS, so-called. Then, to evaluate whether the shape of the deployment shape in which way we deployed them can later play a role in the localization process, we did that for two different deployments, a sparse one and a thinner one, a denser one. And in general, we did that 10 times. So, having collected all our measurements, which can be represented with this histogram here, with spectral colors, we proceeded developing the final ranging model, which is this orange function that we see. Now, to help you understand better how to interpret or what this function shows, I can use the following example. For example, here we have the axis of distance from short distances up to long distances, and here is the received signal strength from very strong signals up to weak signals. So let's go to the slice of very strong signals, and across this slice we can see that the occurrences that happened only at very low distances. So this is why the likelihood there, given a very strong signal, most probably it's coming from short distance. So this is what this function says. So, having modeled now the ranging likelihood and also having collected the measurements somewhere centrally, it's time to execute our algorithm. So the methodology outline is as follows. The first step is to give to each node an initial position. It can be random or 0, 0, anything. Then, after that, we need to select each remote. Then we need to pick the node that we want to start optimizing, to find first, to improve his position estimation. For example, in this case, this is the red smartphone. Then after that, we need to select each remote or neighbor device, all other smartphones, let's say, that have a measurement towards this node, the first node that we selected. And since we have a measurement, we can get the corresponding PDF slides that I was talking previously. So the next step now is to take this PDF and rotate it around the corresponding neighbor. So first this one and this one, those two. Now every rotation has produced a new function. Therefore, the global max of the product of all these functions can be used to locate as an optimization problem where the global maximum is to identify the position of this node. So this step is described by this, to get the global max of the new product of all the PDFs. We used, for example, in our case, the Nelder-Mead approach. And finally, we proceed with the second node to optimize the next node in the row, and we continue with until we have optimized all the rows. But this is one cycle. When this is an iterative process, the method is iterative, and we will continue across different cycles to again optimize every node again. Now, okay, since there's not enough time to explain exactly the steps of this method, area LCL, I choose to explain a bit more the aforementioned rotation that I mentioned, how it works. So by now it should be clear that every measurement is leading to some PDF, like one of those two over there, corresponding to either strong signal or weak signal. For example, some RSS that we received might correspond to this, the weak PDF. Yes, however, since this PDF shows a one-dimensional estimation, we have to expand to more dimensions if we want to go into 2D or even 3D space. And for that reason, the way to do this is to replace the distance variable here with the following equation, and then we take practically the PDF and we rotate it and we create this volcano, and this is one of the PDFs that we have to use in the product. So So at this point, now that we have developed our method, and we also have the other method, the mass spring, that has been so far been respected the most, we would like to assess both, to compare them. So using the ranging model that we developed and also the true positions, we got noisy RSS measurements for both, common ones, and we wanted basically to evaluate at most three variables: how the swarm shape, the swarm size, and the noise level affect both performances. Because we tried to do this, but with a very small number of cases, and we didn't find any good patterns, we increased the cases to have more iterations. And eventually we evaluated 14 million different scenarios. Now, these are, I'm going to the results. Here we're seeing the positioning error of our method at the 75th percentile, and we show both how we show the sparse development and the thinner or the dense development, and how the two dimensions here, the swarm size and the RSS samples, affect our accuracy. So we can see that to begin with, the more green, the less the error. We're talking about errors here, so the greener the better. So in our case, we can see that indeed there is there's a correlation with RSS samples and swarm size, as expected basically, and the more the better. However, we can also see some other patterns. For example, in the sparse scenario where we have less dense cases, in the very big noisy scenarios, when we have too much noise, the sparse cases are affected more because of the in-between distances are further. Now, the same assessing also the mass spring approach, we also identified the same pattern, the same correlation. Now I'm going to show our differences. So here I'm showing the ratio of the reduction of error at the 75th percentile. So basically, the greener the better again here. So this means that at this case of swarm noise, of low noise and big swarm, we improved the 81%, the other method. Yet we don't see negative cases. We only see negative cases here and here, and this is basically because the reason here is because in the 21 case we don't have many iterations, because we have only one case of combination. While, for example, in the swarm size of 3 nodes, we can have many different combinations that we check. So we can identify here that in the thin deployment we had a lot more improvements compared to the mass spring. Also, this scenario can be seen, the percentage can be seen across the whole range, and we can see, so below, let's say, 85th percentile, we introduce improvement, but the results are more or less the same above this. So, indeed, on the 75th percentile, we introduce around 25% improvement. One of the last result is the fraction of improved cases. Okay, so now here we demonstrate not how much we improved in terms of error reduction. We show just here how many amount of cases we had a better result. So, for example, in this case, at 87%, we were correct, and still we see that we are never below 50%. So it means that we introduced indeed, in most cases, improvement. So the optimization, I saw here a figure of how the optimization 5 cycles look like. So every new frame is a different cycle, and at this point we saw the probability according to all the rest of 11, where 11 is probable. And this is the first cycle, and this is the second cycle. So we see how it converges across different steps. And here I demonstrate the residuals of our best scenario, where the green are the true positions of the nodes, the blue are our estimations, and the yellow ones are the estimations of the mass spring. So here, mass spring due to false because there was a reverse problem that I understand it's very difficult for you to see, but there is a problem of reversed shape. So, to conclude, the conclusion that we have with these results is okay, there is indeed a position error for both methods, and it's correlated to both variables of swarm size and sample size. We saw that in sparse deployments are more prone to noise, and that below the 85th percentile, our method introduced an overall improvement, and we have the same improvement, the same performance above it. Also, our method gain is also correlated to swarm size and noise. So the bigger the swarm size and the bigger the noise, we introduce even more improvement. And lastly, our method also depends on, as we saw, of the shape. Although we only tested 2 because of the initial intuition, we we saw this. So the future work is to assess more swarm deployment scenarios, or maybe different, to use the same model across different environments, to use maybe other rating technologies, to fuse other types of signals in our method, and last to take it from offline operator to online. Yeah, so that was my presentation. Thank you all for your attention. It was
Thank you, Dimitris, and we have a lot of time for questions.
Yes, thank you. So I guess that falls into what you're describing under different environment as future work, but what you described was in a classroom,
yes,
with rather flat walls that would reflect in a rather smooth or geometrical way. If you move that into like a landscape with trees, with the cars, what would you
for sure.
expect?
So this question touches how good one can model the signals either indoors or outdoors, which was not exactly our scope. We tried to, because our method requires this, so we had to develop one of those models. But indeed, different environments, we have seen this in practice, can have a different way how the signal propagates inside. Ideally, would be in open space with maybe UAVs and very good omnidirectional antennas, etc. But indeed, this is a specific model for our case. But we could proceed further and even give it a try and check this model to other environments indeed and see how accurate it could be.
Yeah,
But you're right.
In other words, my question is, how much is your model robust to other environments? Because maybe you move somewhere else out of your classroom and nothing of what you have.
As I mentioned, so we have two parts. What we present is basically two parts. The methodology that utilizes a model and the development of the model. So the contribution basically is this part, because so far this approach doesn't exist. But indeed, to create a model, which has happened a lot, there are even generic models for indoor, like that consider how many amount of walls do you have. So there are many different models. This is a question towards this direction: how well you can model somewhere the propagation of the signal. It affects our methodology for sure, but at the same time, it affects at the same way, even less maybe, even more maybe, all the other approaches component to us who are using this. So it's not the problem that we have to face, it's a problem that everybody has to face.
The result you presented are measurements with real device, or it's
from
simulation?
the Raspberry Pis that we selected, that we used.
Okay. What kind of device are they?
So the Raspberry Pis are small modules that are small, dummy, weak computers, like smartphones, let's say.
No, but from the radio, it's Wi-Fi and.
We were using the Bluetooth module of them.
Oh, it's Bluetooth module.
Really low energy Bluetooth.
The devices.
Yes.
Okay.
They're that.
And do you experience the fluctuation of the received signal power
for sure,
versus time? Especially on Wi-Fi, I don't have much experience with
they are
Bluetooth,
they are quite similar how Wi-Fi and Bluetooth behaves, but then for sure there are fluctuations. This is why we try to measure many different times and at different orientations to try to grasp as much noise, let's say, as possible. Yes, there is for sure noise.
You noticed, I would say as soon as someone entered the room that it will be a disaster, no?
So we measured that many times of different orientations. So we introduced on purpose that much noise that basically walking somewhere between, I was walking. was a bit more noise, but we introduced by rotating all the devices all the time randomly. This introduced a lot of noise. Indeed, our random people, because for example, if many people are walking, I didn't have many people there, actually would affect the model indeed, for sure more. But this model is as I mentioned, is something that everybody has to use. You cannot avoid it because all other cooperative localization mechanisms have to use one model. So we use the same model compared to them, which is yes.
Oh, I'm surprised that it's basically so good because we're thinking there is not, based on signal level, it's almost impossible to get such good results.
We can see this is because we tried like different many combinations, like in total 40 millions, and their differences were smooth very extremely highly. We were running this experiment for 2 months basically, and at first we started with 150 cases, and the results were so varying that it was frightening even a bit. That didn't make sense. I mean, it was totally random.
Yeah,
No statistical significance.
I would expect.
Yeah.
Oh, okay.
Let's see first, then.
Yeah, it's still a bit the same question, but because I'm trying to figure out what is the application of this. So unless that would be very good for my kids, who are always losing things in the room, and but no,
Yeah.
I'm joking. But generally, I guess you want to make it for a larger scale, so you want to change like 10 meters as a 1 kilometer maybe, and then you can find your...
So the application here is whenever someone needs to do cooperative localization, and practically this I can imagine it would work best at first in open spaces where you have less noise, and for example not smartphones but drones. But so this is quite generalizable, this method.
But
It
this
can
is what
go
I'm
even
saying.
to
So
submarines.
So basically it would be a larger scale, and then my question is how much, because here you're like basing your measurements on Bluetooth, I guess, or some rather like low distances, physical layers. So do you have an idea how it would change if you go to like, I don't know, 4G, 5G?
So an idea here, and one of the ideas was to experiment with modeling LoRa signals that can go quite far, quite further, and to try to figure out whether and how nice a model we can produce with using this. We didn't have access to that. This could also be further to see. But indeed, signals, for our produced methodology to work, you need a model that is not always flat. It's total random. So it reaches the question of can you find a signal to model it nicely? And yeah, as I mentioned, the first answer in my case would be outdoors in the open.
Yeah, but if you look at you have one picture where you show the I think the probability of
Yes.
your accuracy, or you have range and power. Yes, and you see as soon as if the distance increases.
So basically, more than this,
the
it's
dependence
basically
on yeah.
It's basically, and most of the time the signals are above, let's say 75. 75 is considered actually a good signal.
Yeah.
This was,
But then the distance dependence is almost, if you change by 3 dB, it changed by 6 dB. It changed by 6 dB, and it doubled the distance. If you had 500, you should get 1,000 centimeters. That's 50 centimeters, 1 meter.
Yeah,
and then if you go beyond that, like here it's 2 meter, but if you're talking about 10 meter and 20 meter, you will have the same dB difference between 1 meter and 2 meter, and 10 and 20. That means on the accuracy, you maybe have a centimeter accuracy, but outdoor, with long distance, you'll have meter accuracy.
So how to utilize so one who has a model is prepared of what environments can represent. So if I have a model and I know that above this starts making no sense, maybe I would like to dismiss very low signals. Or this is you have to be flexible. But as I mentioned, not only us. This model is the model that so far all the
well, it's the physics, right? It's the propagation law. Right?
But it's quite noisy and very difficult to be representative to real reality most of the time because of the inclusion or path loss or things like this. But yeah.
Okay, then Antonio, the question?
Yes, okay, we talked already. So my question is that about the computation load of the two methods, right?
Yes.
So I would imagine that the mass spring is much less computationally heavy than computing the optimal point for 20 summations of log normal distributions. Okay, so in order to save a bit of computations, since we see here there is a very high heteroscedasticity of the data, no? So there is the higher the RSS, the higher the lower the RSS, the higher the variance. So we get very little information from log.
You can reduce the effect. So
can you cut the completely the functions associated to low RSS to reduce the computation?
So here we have developed a simulator that does exactly this, a graphical one, and it did as a parameter. We have the effective RSS of the nodes, so we can let the user select at which RSS and load to consider, or the reverse. So indeed, as a parameter, we can filter those to reduce the amount of nodes we have to consider for the optimization of everybody.
So the question is, where would you put the threshold? If you had to come up with an idea where
if I had an idea, first I would have to see my model to see at which point it introduces no sense. But I would like to introduce here to mention here that even low information can be good information, because when you have RSS measurements that are far away, these have the property of pushing the nodes outside. So if you only use very strong signals, you might see an effect that I noticed in also someone in the previous papers. They have also noticed, like mass springs, but they said we don't know why. So indeed, they were filtering signals. The more you don't consider long distances, the more you avoid pushing the nodes afar, and so you shrink your swarm. So I saw this effect. So.
Yeah, and may I follow up with another quick one? Yeah, if you go to the residual, to the last plot where you show the residuals between the mass spring and your method. Yes, so basically in this particular case you are basically completely destroying the mass spring because they have this reflection problem. So the question is, how is the mass spring solution depending on the initialization weights that you put on each mass? So is this a coincidence that the mass spring has this reflection, or is it consistent?
In this result? Case, what I produce our best win for nodes of 21. Reversely, we also have a best loss. I mean, I could easily demonstrate here our also best loss with wrong. So it was not always us the winner. I'm just demonstrating an example of how two different cases can be. However, regarding the initialization, indeed, because they were also facing in the literature quite big problems, it was affecting a lot how the optimization will go on if they had wrong indication. In our case, even with, I just used a 0-0 initial position for everybody, and we were again leading to the same result. So the initialization, we are quite robust there.
So I think there are a lot of additional questions. I have some more as well, but in the interest of time, we conclude here. So thank you, Dimitris, for
So in the last session we have 3 speakers. The topic is IoT. Also the last one is more on mobile networks, and we start with Frederic Montet, and afterwards Christian Göttel, and finally Yann Maret, please.
Okay, so thanks a lot for the introduction, and today I will talk to you about the work we did together with Jean here and my other colleagues. It's a work study called Prediction of Domestic Hot Water Temperature in a District Heating Network, and therefore it's a different kind of network. So first, let me introduce a bit the topic with what is a district heating network. It's basically a big water heater that provides heat for many houses. So it's an impressive infrastructure with all the tubes, etc. that goes in the neighborhood, for instance. It's not new. It started in the 19th century. And today we are the 4th generation of them. And the goal now is to understand the users so that the operator can reduce the temperature of the whole network to save energy. And there's a big problem. If you have cold showers in your home, you're unhappy. And so probably you experienced that during camps when you were like here maybe, I don't know. Okay. Or at home, imagine you have cold water, it's very annoying. And since the district heating network works on a subscription basis, there is an operator that faces the following problems. On the network I worked, there is 170 houses, different humans, different infrastructure, different habits. So how to do? How much heat do we do? Do we create? When? And this is the problem that we have had here. So now, the research question is, in this context, in the context of small households, can we predict the use of domestic hot water with machine learning? Because we are IT people, and there is a lot of data now. The whole infrastructure is there. Can we do something with our knowledge? And for that, we take the following assumption: heating systems and human are going in different states that can be modeled with, for instance, a long short-term memory network or such models. And the goal is to make better loads as an operator. And for that, where is the data coming from? It's from one of those hot water tanks. So the sensor is at the bottom. And we measure the temperature every 2 minutes. And why the heating system? Because so why do we do that? Because it models in the same signal the temperature of the heating system and the user behavior, how the one is using the water in his home. Our method to try to predict, so now we try to predict the water temperature in this boiler, in this hot water tank. And for that, we made a selection of 8 households, because in Switzerland the distribution of households in Switzerland the very small. We took 8 households. All those households are small villas because they are very well represented in the
Swiss Housing Park. Then we did a bit of feature engineering. We did unsupervised labeling of those temperature time series to see where are the moments where the temperature increases, when it's decreasing, when there is a usage, or when the temperature is decreasing with some special heating equipment that are in some houses. Then we modeled with a gated recurrent unit, which is a simpler version of LSTM that is a bit more recent. And we did model all the houses, and we did an evaluation of the model we created hourly on a month. And bonus, now the data has to be chosen carefully in the last years because our behavior in a house did change completely. So it was impossible to take data from 2020, for instance. We had to take data from 2019. So here are the different subscriptions of the houses in that we chose. So they are annotated with a capital letter that denotes the similarity of houses. So this is one semi-detached house with its two parts, and that's why they have the same power consumption. So we took similar ones and up until a little bit bigger ones. Here, some have a device called a circulation pump, that is a pump in the heating system so that the water arrives at your tap warm and not cold in the first 30 seconds. And then the unsupervised labeling was done with first finding the local minima and maxima in the temperature signals. We did then split all those segments in different parts to cluster them in an unsupervised way. And then we evaluated the quality of the cluster with a score called the silhouette score. And it's between -1 and 1, describing the membership to a cluster. 0 means no membership. And given the results of this clustering, it's we didn't make such a. There are not many very good groups. And for the fun fact, this silhouette score comes from the University of Fribourg. So. And for the different models that we created, so we have in total 32 different models that we created with different feature sets. We tried first the temperature only, and then we increased the different features that we gave with the holidays, the weekdays, and our labels, as well as the outside temperature, to try to get some better prediction of our output value, the temperature, in the next hour. On those 32 models, usually we have a convergence like this. So this is the validation loss, this is the training loss. So it's more or less okay, but on 32 different models, we cannot really watch carefully every model training, because it takes a lot of time, and the goal is to see, is it generally possible to do such a task or not? And when we do the evaluation, when we do the prediction using those 32 models, we do have quite good score. This is the MAPE, so the mean absolute percentage error. It's good values, but can we use that? Because if we have such a result in general, it means it's good, right? And the answer is, I don't know. Because in reality, for instance, in the household C1, we see here the temperature of the. So sorry, we see here two households. And in black, the temperature of the real temperature measured, and in blue, our prediction, hourly on 1 day. And we see that when there is a usage, the model has a problem to predict such a behavior. And when there's no usage, the fit is very good. And therefore, with that, we realize that, okay, when there is a usage, the spikes are very difficult to model. So the human behavior is not really simple to model. But the heating system, with or without circulation pump and different rhythms, is something that we can model successfully. Which brings me to the conclusion in summary. So modeling the domestic hot water temperature as a proxy to predict the human behavior is a bit of a hard task. That's why usually the operators use average profiles and such methods to plan their workloads. And the addition of derived feature did not help a lot. It did maintain or decrease our score, so we should try to find better additional features. And the heating system is well modeled, and the spikes are not modeled well. So what can we do next? There are two solutions: better models, more recent ones, or more elaborate methods. And the problem is that we have to use this at scale or on 170 houses. Maybe we have to do retraining when people are moving in and out, and because the training is quite computationally expensive, we also have to look for cheap training, cheap modeling in terms of computational resource. And for that, maybe all the big models, transformers, etc., are not the best ones. So the ideas for the next steps is to use what we did to filter out the human behavior and then try to predict it or make better profiling that are targeted for one domestic district heating network. And maybe then we can make better loads. And that's it for my presentation. And if you have questions, I put a little joke.
Okay, thank you. So we have more than 15 minutes. Questions?
If you say you have to model human behavior,
yeah.
then how much data do you need to gather to because in a way it's very predictive. If, for example, you know that I take a shower every morning and I go to work every morning,
yeah.
but every Friday I have to go to Lausanne, so I don't take a shower, for example.
Yeah.
All right?
That's exactly this kind of...
It'd be quite easy, but then I have vacation and you don't know when I take vacation. So I'm extremely predictive in a way, but you have to be Google to know.
Absolutely.
Google probably know much better myself than myself, right?
That's
so
what we say.
The problem I see is that you don't gather enough data, but maybe you could say most people take a shower in the morning. So on average, if you have enough household, then you need to put so much heat, basically.
Yeah.
But so maybe instead of going through the human behavior, each individual, which is, you will never have the data, and also ethically, I think it's pretty bad, right?
Yeah,
but on average, then it's okay.
Yes, it's on average it's okay. But now we are in this context of that is a discrete context of 170 households that it's very clearly defined, and so we have to
to see how are the users behaving in this very context. We cannot take all their data. We have to do we have to take what we have and then do something with that. So we now have it's a big infrastructure. Imagine 170 sensors connected to all the boilers in all the houses. There's a lot of manpower that has been used for that, and so far we had 3 years of data every 2 minutes. And for this study I used 1 year to predict 1 month. And the result, so it has some problems because we don't have many yearly seasonalities that could be beneficial to predict. For instance, vacations taken at the same times. But yeah, we do have to. Maybe the direction is to make better profiling and to make some average with all the prediction we have, and that can be better than wrong prediction of a usage spike at the wrong moment, but close to it.
No.
Does it answer your question?
Yeah, that's true. I kind of forgot. If you want to predict this spike, but you cannot say, okay, in this hour, basically, I don't really care. The spike arrive only in the morning, between 15 and in the afternoon, the ranges.
Yeah.
And then you don't care where exactly the spike occur, but you know that like maybe 60% of the time in that range you have a spike.
Yeah, but that's the direction I want to.
Okay, yeah.
Just a question on this figure. So if you have these spikes to the bottom, does it mean that in that case there was some consumption? And
yes.
The hot water was taken away in the
exactly.
water. And it somehow looks you often are not able to predict these spikes.
No, it's quite hard.
So I'm wondering whether you might think about deploying additional sensors, for example.
Yeah.
A sensor in the bedroom and to measure when people get up, for example.
Yeah, that's that's possible for sure. Then, as a user, do we start to have some intrusive technology, and that's also not the very goal of this.
Good.
Yeah.
So
No.
Quickly, you mentioned that you couldn't reuse data from another year for the prediction. You had the patterns are changing quite a lot. Is it on a small granularity or on a large granularity that is changing?
So we took an assumption to do that. The behavior of many people did change during the Corona period last year.
Okay, so many people change their operating behavior with respect to heating.
Yeah, it's an assumption that has been done because many. So we had the semi-lockdown, and there were some quarantines ongoing, and events that happened way more in houses than previously. And what we want to model is the so-called normal life that happened before the Corona period.
Okay, makes sense.
Yes.
So I want to ask a question more related to more than the technical part, more on the application.
Yeah.
So let's say that you achieve a model that can actually guarantee 99% of accuracy. So you just maybe mispredict one cold shower every 100.
Yeah.
So is this still, do you think some user would prefer spending a bit less money for keeping the constant temperature of the boiler and have randomly extracted the cold shower every 100? So you see what I mean? Could be more in this area of critical system where you don't want.
For that, I think as a user, it's a very personal decision to have cold shower or not, to wait 1 minute or not, and throughout your life, you probably go through different stages where you like more cold and warm, or different period, and you are more able to handle such cases. On the side of a district heating network operator, your goal is to use as less as possible heating energy to use the whole network, and therefore, for the operator, such people could be beneficial to reduce for lower costs for them, because also when you eat less as an operator, your network can last longer with fewer maintenances. So it's also a lowering of the costs.
So it's the user that has to kind of agree that it might be sometimes the...
Yeah. Yeah.
Okay.
Other questions?
Say more about deploying more sensors in the user's home.
Sorry, can you speak a bit louder?
Sorry. On the same notes about deploying more sensors in the user's homes, how much context information can you actually extract from what you have, like timestamps and temperatures? Is it possible to augmentate this data somehow?
We probably could on a per user basis. For instance, if let's imagine a heating service or district heating operator providing an app that allows the operator to know when the user would like to have hot water. So there is a better synchronization of offer and demand, let's say. Otherwise, now with the currently deployed infrastructure, we can have more information in the house, but also they are very targeted to control the behavior of the heating system on the side of the district heating operator and a little bit on the side of the house. So, not many. Yeah.
You mentioned already, but these two households, are they using the same trained model, or is the model personalized per household?
So here I made 32 models. So every model, so there are 8 different households, and for each feature set and each house, there is a specific model that has been trained for this house with this feature set.
Here you show 8 different households, and you said initially you have 172 households. How did you arrive to 8?
So, given the distribution of households types in the 170 that the network is composed with, I selected the 8 that are the most common in the distribution of household types.
So what method did you?
For that, I just looked at the distribution of households types. Any more questions?
Okay. Then, otherwise, thank you again.
Thank you very much.
Thank you very much. So, my name is Yann Maret. I'm a PhD student at Edge University in the UK.
I'm working at the engineer school in Fribourg under the supervision of and in this talk I'm going to present how we can improve the performance of MANET using reinforcement learning. So for the agenda I'm going to talk a little bit about what MANET is, the problem statement, overview of current solution, latest investigation and results, the conclusion about our proposed solution, Meielisalp, which is based on a solution already proposed in the literature where we made some changes, and next step including GNN and our simulation automation tool. So for MANET, it's this main mobile ad hoc network. So basically, it's used for tactical or mission critical communications. Those type of network doesn't rely on any infrastructure, and they are self-organized. And we have such an example. We can think of a V2V, vehicular to vehicle network, flying nets, device to device. All of those type of network are known as MANET. So for the problem statement here we have a little movie about the Anglova scenario, which is our benchmark, the scenario we use to assess the performance of our proposed solution. And as we can see here, we are dealing with 24 nodes moving from north to south. With different topologies, so sometimes they are fully meshed like this, and sometimes at the beginning they are more in inline configuration. And what we want to achieve is to get optimal performance on virtual machine, and actually we do emulation. So basically we have to find something in the middle to improve the performance and to get good results, such as improving the throughput and lowering the delay. More formally, for the problem statement, so we consider two approaches here. We have an omniscient solution. We can, which with this solution will get us close to the optimal solution, and then we use reinforcement learning to understand better the MANETs, considering all the aspects with the radio and configuration, how we can improve the performance with quite a complex topology. And to do that, we can first identify the user traffic, but we consider all-to-all configuration unless the user traffic is provided. And I've been working on finding the optimal path, so improving the routing protocol. And last but not least, we consider as well optimizing the radio TXRX, so the schedule. In this case, is the TDMA schedule. We can have a discussion about it later, but it's a future work. And so I like to present this slide about reinforcement learning. So we have the environment here, the agent, taking some action based on observation. And in this case, I'm presenting the ODR, omniscient extra routing. So it's not directly an agent, but we would like to map the algorithm we developed in order to get to achieve the optimal performance. But yeah, not quite yet. With this kind of representation, we have the environment and the node. And what ODR does is to take an action, so the routes. Basically, it updates the routing table, and then we do not consider a reward function or reward because it's already computed based on observation, which is the graph. So we already know what is going to happen next using only the topology for now. And then we have a similar representation of 5 versions using reinforcement learning. And in this case, of course, we consider a reward in order to train our model. And we have 2 versions. Actually, one used the link state, and another agent used the routes instead.
Another idea, more recently, is to invoke a bird's eye view. So clearly what it is to give more information as the observation to the agent in order to make better prediction about the link state. And in this case would be to use we already know, it's possible to know at each given time the position of all nodes, considering the user of this blue force tracking is the kind of protocol to share among all nodes the position of the nodes. So about the current approach and restrictions, as I mentioned before, we consider all-to-all if it's not provided the user traffic. And in the case of the routing protocol, we use OLSR or ODR, and the idea is to improve the performance of OLSR or even applying new routes to the environment using the reinforcement learning methods. But yeah, and we have seen quite strong relationships between the routes and the schedule, so it's a good idea to investigate further into the schedule TDMA to provide even better, to enhance the performance of the manet. And here it's a quick summary about the method. So we have ODR, which performed really great. I have those couple of slides talking about this one. Then we implemented a few what we call OLSRQ, which is based on a Q-learning algorithm. Like we have here a simple Q table. And more recently, we see in the literature implementation using deep reinforcement learning, and more recently, and the trend is to use a graph neural network to improve the performance of the routing protocol. Since routing protocol and routes are quite really similar to a graph. And as I mentioned before, we have Anglova to assess the performance of the proposed solution, which is really complex and dynamic topology. And we took a subsample of this Anglova, which we called 902. Actually, it was the idea of Macaulay in their paper to use this network to test the performance of the algorithm. And the idea, I can move on the next slide, is to avoid the congested node here. So we have a node here in the middle, node 1, and if we consider the bidirectional user traffic between node 2, 5, and 6 and 9, one with typical solution like OLSR, like ODR even, we will route all the traffic through the middle node, and then it's already congested, and we can reach good performance using the central routing. But when we move to avoiding routing, that we have to detect alternative routes. It's possible to increase by 2, so 83 kilobits per second in the theory, the throughput. And last, we have seen this in the simulation that if we oscillate between avoiding routes and central routes, it's possible to even increase this throughput. But we have to change the route at a given period. Otherwise, we degrade the performance and we end up in between here. And then I talked earlier about TDMA. And in this case, we change the schedule, the TDMA schedule, so it's time division multiplexes. We change the schedule to give more resources to node 1, and by doing that, we can increase the throughput. And if we do even more work about understanding this network, we can set up a schedule which is called slot reuse, where in a given slot, we schedule more nodes to exchange information. Just a brief overview. Once again, the overview of the agent I'm going to talk about. We have the agent and mainly the differences in the action, either link state or other routes. I'm running out of time, so I will just present really briefly the agent. We have a few agents. The two first are not reinforcement learning agent, and 1, 2, 3, 4, 5, 6. The sixth last are reinforcement learning agent, and we have a good performance of OLSR D2 ODR in the Unglovas scenario, and on the 9-node Turing, only the three last are able to detect the avoiding routes. And I would like to just to introduce this slide. It will be the structure of the upcoming slides, where we see the observation, action, reward, results. So for LSR, we do not have the reward, but what we observe is the link, either connected or disconnected in the network. And for the action, we consider the airtime. Basically, LSR use the DAT metric to create or to find the routes in a network. And with this method on the Unglovas scenario, we reach a completion ratio of 70%, and but a poor result on the 9-node Turing topology. For ODR, we have quite similar performance on the Unglovas, the 9-node Turing, because we are not able to find for now longest, more a path with more hops. We can only see the same amount of hops, alternative path with the same amount of hops. This is because we cannot increase the throughput in such a topology. But 94% of completion ratio in the Unglovas is really interesting. And then it's one among the others. Proposed solution, which we call OLSR Q3, and the idea is to inject another airtime into the OLSR, the underlying routing protocol, to make better prediction. And what we observe on top of that is the queue of each nodes. And by with the help of this observation, we can make better prediction about the airtime and increase the throughput on the 9-node Turing, for example, with 50 kilobits per second. And now I just want to take some time about upcoming work and what we can do or what we can achieve with deep reinforcement learning. So similar to previous slides observation, in this case they consider only the traffic metric, so this is based on Stampa's paper, and they do not need to know anything about the network. So one limitation about this implementation is that it's will work on just one topology, and if one node is shifted away or even out of the network, it won't work anymore. But the action is the link weights matrix, which is really interesting and can be seen as the airtime between two nodes. So it's a good, I think, good action. And then they have the network delay as the reward. But I do not want to spend too much time, and I just want to bring the idea of graph neural network applied to routing protocols. We have had a presentation earlier about graph neural networks, so I will just give my thought about it and how I understood. So basically we start, let's just talk about the scenario here, the environment. So the idea is to find the routes. So the agent is a packet, and we have router here. And the idea of the one agent or the packet is to move from the source and to find a way to reach the destination. And when we reach the destination, well, we give to the agent +10 as a reward, or if we enter an overloaded link, so basically we have a capacity or a limited bandwidth per each link, which is not really what we expected in Manet, but it's their scenario is implemented this way. Well, we have a reward, a negative reward. And for the observation, we have this as we call ending or feature vector with the information about the agent. So the agent is the data packet, and inside here we will have information about this packet. So on which node or on which edge the link the agent is, and the packet ID, as well as size in bytes and destination ID. But the same for the edge, and with that information, then we can feed the model in order to make prediction on the 4 action, which is the most interesting action to take. So we can even take hold. I mean, the packet will stay on the router, or take gateway 1, 2, or 3. And yeah, well, with that with this concept, they have shown that they can increase the performance and find alternative paths and avoid congested links. In this case, not nodes as we would like to do. I don't have much time, so I will leave this like this. I'm not going to talk about. It was another interesting idea about graph neural network to solve similar problem. So in conclusion, what we have seen is that OLSRQ is not optimal for the Nova scenario. It's complicated to generalize just using just a Q learning algorithm for larger network and user traffic scenarios. What we would like to improve is ODR. We would like to find alternative routes with more hops, but currently we can only find alternative path which has the same number of hops as the shortest path. And yeah, graph neural network seems promising to improve the performance of the routing topology, at least in software-defined network, and we see in Manet as well. Thank you.
Okay, questions? Yes. Okay. Thank you for your talk. I have I'm confused why the omniscient Dijkstra, which is basically it should perform in the best way because it knows everything. Sometimes performs worse than the Q-learning based approach. I know that is because it doesn't have information about the Qs, right? But at the same time, I would expect that it would be fair to have them run with the same information, right?
Yeah.
So why? I mean, have you thought of running the generalized omniscient Dijkstra with the same information basis as the?
Yeah, so it's yeah, you're actually right. So it's the next move. Actually, when I talk about ODR, the improvement about ODR is to have to look at more routes and find, in this case, the avoiding routes with the help of the traffic. Maybe we'll see if it makes sense to include as well the queue information later on.
But this work for sure has been published because I have worked on this. So there is you can modify the weights on each link to include the length of the queue. So Dijkstra will still pick the shortest route, but modifying the weight of the. So it would be short in another way.
Yes, exactly. Can do that.
Yes, maybe the others first. I have more, but maybe the others is better.
Maybe continue.
Yeah, no. Okay, regarding the paper that you said you published in BTC Fall, what metrics what did you measure?
So in this paper, how we measure the throughput, actually how.
If you have, it would be.
So what we did here, we evaluate the OLSR ODR mainly on two topology. Was the Anglovas scenario and one version of the Anglovas scenario, which is the static. So we took the first second of the Anglovas scenario. If I remember correctly, we have the published results about how those agents, if I may, ODR and OLSR perform in an urban scenario. And what we have shown that is with using ODR, it's possible to do a load balancing. So in this context, it's possible to get a higher throughput than using only OLSR. And completion, yeah, we have also information about the completion ratio. So it was another metric, so mainly throughput and completion ratio.
So mainly throughput. Okay. Did you measure the overhead in the sense the number of messages? Because OLSR is like famously heavy on the overhead side, especially in BANET. It's just impossible. Have you compared, for example, there must be some entity in the network who needs to compute all of this, right? So is it a distributed algorithm that does this? Is it a centralized control that has to collect this data from all the nodes? So first of all, who actually does the computation of these optimizations, and how the information from each node of the network reaches this entity that does the computation?
So are you talking about ODR or
any of these?
Okay, so for OLSR, we didn't really measure the overhead. I know there is plenty of paper explaining OADV and which one is the best, considering this kind of interest. But for ODR, yeah, for sure, we need to have the overview of the whole topology in advance. And for each given second, we compute the best reward. The best route, considering an all-to-all user traffic, which is not really the reality, but we made this assumption that it should be close enough to the reality in terms of user traffic. And what was your last question?
No, maybe
how is the information from the network reaching
well, with ODR, we are completely omniscient, so we don't care. It's not feasible. It's an algorithm that's for benchmarking purpose, so we don't care.
Right.
But for OLSR, they have this hello packet and the topology control, and so they have a lot of overhead. And what we did is we reserve 1/4 of the entire bandwidth for traffic management. So it's quite a bit, it's a lot, but in tactical network, it's basically you can say maybe it's not normal, but it's better to reserve, you want to have a full control.
Yes.
So we reserve, and that why it's 1/4 or not more or not less it's by experimentation. So it's on Anglova, on this particular scenario, it seems that it works well with 1/4. But we did not investigate, the trade-off or all that thing.
Yeah. Also, the diameter of the Anglova is maybe 2
exactly,
or 3 hops.
Exactly.
Already, OLSR has information 2 hop neighbors because they hello and the answer for the hello. But what happens when it scales to a CD BANET and then link state protocols? You need to send these TC messages. You have to float them, so it's quite intense traffic.
It seems to work for with reserving 1/4, It seems enough for that particular scenario, and it's a benchmark scenario that can say everybody's using instead of the randomized usual scenario. So he's using that and not questioning that ratio, basically.
Okay.
Yeah. But it's true. It's one more, again something to investigate. Additional complexity if you want to really optimize everything.
Yeah. If there is any other
maybe I have one. I didn't quite understand this global scenario. So can you maybe
remove it?
For example, what is these are what is happening there? So what are the moving objects and what are the link speeds?
Okay. So this scenario is recorded in Norway or some place like that, and I don't really know. But the idea is to record each. We have position each second and of each individual nodes, like we have here in this case 24 nodes, and the moving speed average is around 50 kilometer per hour, because they are vehicles.
But it seems that there are always groups of nodes. So, for example.
Oh yeah, because it's tactical scenario, and usually they try to stay like at least three of them should be next to each other. So yeah, it's a tactical scenario. I didn't question him why it's this way. But
under using what kind of network technology it's.
So it is up to us to emulate what we want on top of that. It's just we have the position, and that's it. And then we can propose a performance, and based on that we have to define what we use. This model radio, we use this routing protocol.
Okay. So then you can vary the link speeds.
Yes, and the pass loss is computed from the graph, from the position of the nodes.
And for your machine learning based optimization, so what are the input parameters you are considering there?
Okay, so well, we can consider plenty of parameters or observation, but so far what we have done is include only the Q, but we can think of giving the position x, y, x, and y of each node. We can even, as shown in the last slide, user traffic. No, we have a lot of, but we're trying to just understand which make more sense to give.
But as far as I understood, you use a lot of simulated data, not from real world, except the mobility.
We assess the performance of the Angular scenarios using the solution. We try to set up, but we emulate. We do not simulate. We prefer to emulate with the model of a real radio used in military.
Okay. Other questions?
I cannot find one.
You have the privilege.
I wouldn't.
The last question here.
Yeah, I would wait, but there is. Okay, so one thing is, so let's say we start from the baseline of OLSR. No, for example, we could think of augmenting the already working protocol, for example, OLSRD, which has some information about the congestion as well. I guess then we have some delay between the moment in which the information about the congestion is propagated from each node to every other node. Let's say this is some sort of delay. Then I would imagine that your machine learning algorithm is better. It aims at removing this delay by predicting how this congestion, where will happen. So what are the scales, I mean, especially in small tactical networks like this, I would imagine the propagation of this information is quite quick. So how much do you actually gain in terms of the speed at which you can predict this congestion compared to just communicating after the congestion has happened?
So this information is broadcasted by OLSR. We just
yes, you flood.
Yeah, we change the DAT metric, and everything else is done by OLSR. So we shouldn't have more overhead than regular OLSR.
No, I mean the delay between. If you predict, you don't have to actually communicate the congestion level from one node to the others because you've predicted.
Yes, exactly.
So how long is, especially in this particular case that you simulated, how long was this time that you saved?
I'm not sure if I understand.
No, we didn't look into it. Yeah.
Okay.
We basically we are using OLSR with standard parameter. Like he mentioned that we used it changed the route only every 5 seconds.
Oh, 5 seconds.
Yeah, and we get better result if we do it with 2 seconds. But we didn't look at exactly, how the topology propagates.
Okay.
We basically we didn't care about. We just took OLSRD, implemented the open source software, and that's the beauty of emulation. That we don't. It could be it's a black box for us, and we just give them. We are changing the link state, right, through the machine learning procedure. But actually, we are not faster than what OLSR is already doing. We are just basically cheating on the link state estimation by you. And actually, we are not even predicting and that's maybe actually it's a good idea. We are not really predicting the future congestion. We are just adapting the link state according to this queue, the queue level.
Well,
that may be why that's a very good idea.
Not mine. The literature.
Why,
there is a lot of congestion prediction.
It's not performing very well, as you have seen.
Okay.
Thank you.
Thank you. Yeah.